Alrighty, we're live for part 8 and hopefully the finale of my Synacor challenge run. Um, it'll be a late night otherwise. Anyway, we left off with a couple of big unresolved threads. So the big one is the vault. Oh, let me get my whiteboard working properly there. So the vault here. This is a little maze in the game where you hold an orb, and as you're holding it, you write an expression and evaluate that. And you have to get it to the value of 30 in the minimal number of steps. Um, so with that one, well, we can talk about that in a bit. So there's the vault. Um, there is the Ackermann function. Um, that we need to find the correct input for. So this is the thing that uses the value in register 8. Um, Basically, I just bypassed that by giving it the value in register 1 that needed to go ahead and jump past the branch. So I haven't actually done that properly, but I know what it is. Or I recognize it for what it is. So we can figure out how to reverse that, or I don't know, we could just run it. We could run it in a worksheet and find the right value. So that shouldn't be too bad. Um, Now in this vault, I had started a Dijkstra, technically just a BFS because all graduates are one. Mm. And we were having some issues, so it was going too deep. And what I think might be happening there. So there are a couple of things. We're not filtering off branches in the right way. So it's the overflows and the negatives. So I started trying to represent these as the Synacor 15-bit unsigned integers. And I wasn't exactly sure how to handle negatives, and I left it at that. And I think I might go in and just try that with ints. I started extracting the bytecode so I could see what's happening here. So I extracted the bytecode for when we just do a -9, and I compared that with when you're holding the orb and the math runs, and when you're not holding the orb and the math doesn't run. And I found stuff that looked like it was doing some sort of overflow, um, like overflow management of some sort, or at least it was showing interest in, you know, the sign bits. So it could be the case they're doing that for me, right? Or it could be the case I might need to do something similar. I don't think I necessarily want to re-implement all that mechanism though. So I'm gonna look at how the numbers change and grow. I'm just gonna use ints. And if I have to handle an overflow, we can do that. One True Bob, hello. Yes, it is time to finish, I hope. You don't Oh yes, you recognize this diagram. I have another question for you. Welcome, Dave Eddy. Good to see you here. Do you recognize this diagram? This is the twisty little passageways. It's not actually too bad. It's just these arrows, like all of these arrows going back to this one, and like this one that looks like it's going north, loops like you go south and north, and then you go somewhere else altogether. Yeah, yep. I just mapped out how that's going, and I decided early on that I was gonna trust that they all had distinct names, and then yeah, I just mapped out the nodes. Um, and the initials are, this is a maze of twisty little puzzles. This is a twisty alike of little puzzles, all maze, or little passageways. Sorry, I've been mixing that up. My go live notifications have become maze of twisty little. bytes, all code, something like that. And I've confused myself, so I forget what the actual words are. Yeah, yeah. It turns out the names are unique. Um, yeah. So that's the plan for today. We're gonna go to the Ackermann function and reverse that. Then we'll go revisit this and figure out what to do with the overflows. And I might switch back from using the U15 to just doing it int and see what happens there because I think I wasn't handling the negatives properly here. I think I recognize it nearly right away. It is cool. There's a lot of fun links to click on in that Wikipedia page. Um, so with that, let's get right to it. We don't need to go into the console yet. So let's pull up one of our worksheets. Um, and we are playing around with uh, here, one of these functions here has the output we're interested in. So this is, actually, where is it? Where's my notes here? So that's an XOR function I found. Um, this is 154b plus 3. I don't know where my note is here. It's missing, but I think R8 is used here. Well, this here is an Ackermann function. Nope, that's not the Ackermann function. Oh no. Uh, um, is it this worksheet? No, this is playing around in the vault. We're not gonna look at that yet. Anyway, we at least have my Scratch files where I was looking at these. So the Ackermann. Okay, so it looks like. Oh, this is what happens when you take a big break and don't leave notes. Okay, so for some context here, I did two different things. So in my console, I can run I can log the ongoing bytecode, so the running bytecodes live. Um, and what I'll do in these worksheets here is I'll take one of those, and then I'll look for functions of interest that way, right? So here I have my log of all instructions that will run, and I look for anything that contains R8, right? And then 15154B. So this is an address of interest. And then what I do when I have these addresses is now I look for the addresses that are being called, and then I'll just extract that function. So um, I have some functionality that extracts these functions here. So that one that we were looking at, 154B, that is the address where um, we jump if the eighth register is false, right? So if we look a little bit after that, plus 3, this must be a function that appears shortly after that. This might be, no, this is not the Ackermann, but it does call the Ackermann. So if we look into this, we call 05B2. That's it. That's the Ackermann function. And then after that, some time later, there is a jump. This is in my code, so I hard coded here an escape. So we'll open my VM state. Alex, hey, how are you? Good to have you. Okay. So here, I have a special case here. When we see this address, we don't call the function. We just store in register 1, 6, because that's what's expected in that register. 178B. Yeah, and there's a function here to extract. Let's see what the value is. Okay. Oh, so this 178B then is the actual Ackermann function. I just don't know why it's not. Oh, you know what? You know what I did? I figured it out here. Um, this isn't my source of truth anymore. Alrighty, here it is. Here it is. So my original version of the extract function would stop upon a return. Now it does that based on if there's a call, you have to still have more returns to make up for that. Um, so this here is what gives you that, and we can just get this worksheet. We can just get this output, and I think I saved it to Scratch. 178B. Okay, 178B. Okay, and here it is. So here's a function from the infinite loop. This is our Ackermann function. And what I want to do here, oh, whoops, 178. What I want to do here is just implement this in normal code. So we'll pull up a worksheet and do that. So def acc. In fact, let's just pull up the Wikipedia page. So Wikipedia, here we go. And we'll look for a definition just so we can kind of see how this works. Instead of just trying to implement it from the bytecode. Like this might, I'm just gonna trust that that's the same thing for now. It looks much like the same thing. So we have an M and an N. M int, N int, turns an int. Oh, we've got Copilot doing this for us. Copilot definitely knows the Ackermann function. And then we can do a match. So M and match case. If we have 0 and N, we return N plus 1. And if we have M plus 1 and 0, let's see. I'm just going to do like an A and a B. No, we're going to do it this way. So if you have an M and a 0, then we're going to return Ackermann of M minus 1 and 1. Right, this is just a non-zero number, so I'm just moving the plus 1 over to the other side. And otherwise, if we have an arbitrary M and N, neither of which are 0, then we have Ackermann of M with the Ackermann of M plus 1. It's just going to be M. Hold on, this is M minus 1. You gotta remember we don't have plus 1s on the left side here. So this is M minus 1. And we have the same M. And we have N minus 1, N minus 1 here. Okay, so we can at least try that out for a few values. We can try that for small values. So let's try ACK for 2 and 2. That seems fair, yeah. 7, not too bad. Let's try 3. And there's a lot going on this worksheet. Great. So let's try and figure out what the Ackermann function is actually running on in the bytecode. So let's open up that Scratch 2. And the O5B2 function. Where is a call to 0x05B2? That's here. Okay. Right. So this is the place where we have the Ackermann skip. I'll just pull that up for reference in my VM state. Down in the bottom left, so Ackermann. Okay, so if there's a call to Ackermann, where's the actual call to it? Call to, okay, here. Call Ackermann. Then what we do here is we store in R1 the value 6. And the reason we do that is because we have a jump faults right here. So O06A. What is R2 here? So we set R1 to the value of 1. Jump of faults R2. You know what? I'm not sure where I got that R1 being needing to be set to 6. I'm sure there's like a jump if equal. Okay, anyway, we could at least, what we came here to do is find what it's called on. Okay, so if this here is the well, where's the Ackermann? The function from the infinite loop, yeah. So what is it treating as m and as n? So in this case, n, the second parameter, is the one that's incremented. And then m, the first parameter, is the one that's decremented. And then we have n set to 1, the one that's first checked against 0. So we jump true if this is not set to 0. Okay. So R1 is one of these. Otherwise, we add 1 to R2. We add 1 to R2. And then we save it as a value of R1. Are we kind of swapping directions here? No, that wouldn't make sense. And then we set a value to 1. So where does that happen? So there's a set. Oh, there's a set R2, R8. There's a set R2, R1. We add R2. I mean, anyway, in either case, it seems like R2 and R1 are our parameters. So if we look at what R2 and R1 are set to, R2 is set to 650. That's huge. And R1, it gets set to 1 afterwards. Why did we set R3? R3 is never used here. When's the last time R1 is set? Read from mem. Let me see. Let me just check my read mem doc. Read memory address B and write it to A. So in this case, read the address in the register and write it to the address in the register A. Or I mean, write to register A rather. Okay, so we save that in R4 and R5. We check if R4 and R5 are equal. And jump a false. So we jump down to 6AF, where we set R1 to 0. Hold on. This OX5B2, that's not calling Ackerman. What am I doing? That's why we're confusing ourselves here. That's not a call to Ackerman. We are looking for 178B. OX178B. There it is. There it is. Okay. This makes a lot more sense. Okay, we set R1 to 4 and R2 to 1. Okay, cool. And then what happens in the end is we're checking if R2 is equal to, or we're checking if R1 is equal to 6. We're expecting that to be 6 at the end. I don't know why that makes sense, why it should have like a leftover value. Right before its final return. Well, let's see here. What has a straightforward return? So this one is the only non-recursive case, right? This A0N. So what that's telling me is that in the final call, R2 was 0 and R1 was 6. Right? Or 5. And that's what but no, as it pops back up the call stack, those would get overwritten. So I still don't know why that's equal to 6, but we do at least see 4 and 1 being passed in here as arguments. So why don't we take a look at that in our worksheet? So def ACK. Okay, ACK, and you know what? Let's just try both ways. So ACK for 1. 4 1's going to be pretty big, I think, because 1 4 is going to be pretty small. Let's start with that. So I doubt it's 1 4. And just, yeah, right. 4 1. Okay, so R1 is our M, and then R2 is our N. Dave, I saw that you finished, by the way. So I'm hoping this means that this can be my last stream. But yeah, congrats on that. Okay, we'll give that a second to run. I mean, that's a big function on its own. Maybe I don't want it running in the... Is this assembly? Yes, this is, well, no. Yes and no. I'm kind of calling it assembly, but this is the instruction set for the virtual machine that Synacor runs on. And this VM has a stack, it has a bank of registers, and it has memory, and so it has like a bunch of operations for interacting with that. So you can call it assembly, and then you'd have to translate down still into some sort of machine code. Hoping it's the last stream. You've got to beat bad cop to build a C to Synacor VM compiler. No, I don't think I'm gonna do that. But I do want to do other things with it. So there are two projects I have in mind. One is I've already written all this in Scala code. I want to just dump this into Scala JS and run Synacor in the browser and just have that be my interface. Can make it all nice and pretty and whatnot. In fact, I'm kind of wishing I'd done that as a little side quest earlier on, so that you all could play along while I'm doing this. Um, but that I think it shouldn't be too bad because I've written everything. I just basically put an interface on top of it. And the other thing I'm thinking about doing, if you've heard to Nant Tetris, so that has a stack-based virtual machine, which then relies on an assembly, and it has its own like hack CPU architecture. And those are all very like nice and like self-contained, really easy to implement. um, what I would do to translate this to another architecture is just squeeze this in to jack/hack at the VM layer and implement the jack VM on top of the Synacor instructions. And I think that should be pretty doable. And I've already written a compiler for Jack, and at that point, now I have something that compiles down an object-oriented language to Synacor. So that would be my idea. Um, but also further down the line, I think I'd like to revisit Nant Tetris. This here never ran. So what I'm just gonna do is paste this into a console. So there we have an Ackermann function, and we're gonna ack for one. Okay, that shouldn't take as long there, right? Yeah, 65553. I'm not sure what to do with that value. Okay, if this thing was like a reverse Synacor, 65533. Res1 and res0 dot 2 hex string. FFFD. That's nearly the max value. Oh, and that's 16 bits. That does not fit into 15-bit. Okay. Let's leave a note here. So Ackermann of 4.1 is equal to FFF7. FFF7? FFFD. And that is not U15. And why is it expecting R1 to be 6 here at the end of all of that? Okay, we have to look at where R8 comes into this. So, let's see. We started writing a translation here, but I'm just going to like comment into this assembly on the right. Krypton, welcome. How can a beginner start reverse engineering? Any good resources? You know what? I basically just sort of started with Avon the code puzzles. So there are a few puzzles in particular. Look at 2021 day 24. Is it 21? No, 2022. 3, 4, 5. Yeah, 2022 day 24. That was the first real reverse engineering problem I did. And that one definitely took me all day, but it was a fun one. I think in general, Avondale Code has a handful of reverse engineering problems, and you know, they're all like toy-ish problems. So that's a good place to start. Oh yes, yeah. Thank you for suggesting those. Also, 2019 has a lot of 2019 has a lot of problems around an encode machine, which is very similar to Synacor here. And what you could do is run through those puzzles. Like the first few are just like implementation, and that scales and gets like progressively harder. So you're just doing normal engineering, and eventually you're doing reverse engineering. So like that might be a way because then you'll understand all the pieces because you've been working up to it slowly. But yeah, speaking of reverse engineering, what is going on here? Uh, so we need to figure out how R8 is even used in this implementation of the Ackermann function. And what I'm going to do is annotate this um, so I can actually kind of see what's happening. So in this case, so jump if true, jump if so if R1 is 0, R1 is equal to 0 right now. Um, so R1 is equal to 0, and from there we set R1 is equal to, we set to R2 plus 1. Um, and why did we switch those around? And then that's it, we return. And I suppose then R1 comes out as the answer. Wait, hold on. Is this expecting a 6 because of overflow? I mean, I'm not sure that would make sense. Right? Like if we did FFFD minus the max value minus 7 FFF. Or if we did like, I suppose if we did 6 plus the max value. And then 2 hex string. Yeah, we'd be barely over. Um, well, okay. Let's look at this here. R1 equals R2 plus 1. And then we return. That's it. In this case here, if R2, then go to that else. I want to turn this into something more like my code. So we'll do like three cases. So more like by my code I mean this implementation on this lower left, because this is much easier to read, right? Um, so we look at R1 and R2. So case 0 and R2. In that case, R1 equals R2 plus R1, and then we return. Otherwise, if we have R1 and then R2 is equal to 0, so if R2, we skip ahead to this one here. And in this case, R1 equals R1 plus 8, R2 equals R8. Why that R2 equals R8? That is what's happening here, right? So add to R1, max value. That's essentially -1, right? Yeah. So we're essentially calling, if I were making this a more functional version, um, yeah, so we're going to recur then with it was essentially Ackermann of R1, so R1 minus 1 and R8. So this always becomes R8 every time we call that. Every time we're in that branch. Um, and I suppose if R1 is just being used as a result, then it's fair to write in the value of that. Oh, this is just +1. So we just return R2 +1 is what we're doing here. Right. And then we're saving it to R1. And it's not like we're flopping values there. Okay, this is starting to shape up a little bit. And now in this final case, you're sad it's my last stream. You want more pure coders? Well, it's not my last stream forever. It is a stream in which I'm hoping to finish the Synacor challenge and get all of its codes. But there might be like a part 9 out of 8 where I make this whole machine nicer. There certainly be like more to this. I mean, in my README here, I have a whole to-do list of things I want to do with this. So it won't be my last stream, but I appreciate it. We have the case here, case R1 and R8. No, R2, where these are variables. Now here, what's happening? There's 2 recursive calls. So R2 minus 1, so that's like the n minus 1. And let's confirm this recursive call has R1 and R2. Why is it pushing R1? Right, it pushes R1 because we want to save that for the other recursive call. But why is it doing this recursive call first? So there is a recursive call. I don't know where that's going, but this recursive call here is R2 equals R2 minus 1. Oh, why am I writing this here? I won't be messing with this. So there's a recursive call where we have R2 minus 1 as an argument. And the first argument to that hasn't been set yet. Because the first thing we do there is we push we push R1 onto the stack. We push the value of R1 onto the stack. And then we call it recursively. Okay. Then we set R2 equal to R1. Then we save R1 and we save this R1. So the recursive call gives us a value. And we save that in R2 before we pop. So R2 is going here. Okay, I see it. Right, so R1 then is the result. Like that's what's going on here. That's why we set R1 equal to R2 plus 1, because we are saving the result in R1, and then we return. This is the branch that doesn't ever recurse. Okay. Right, so this is the inner bit. I don't know what's there, but this becomes, so this becomes R2. ACK and R2 in a new call, where R1 is just R1 minus 1. This is the R1 that we pushed and popped so that we wouldn't overwrite it. So R1 minus 1. And the ACK here was value of R1 when this call is happening here. Well, just because we push R1 doesn't mean we actually change the value, right? So that's just R1. Yeah. The register value is still the same even if we are saving it on the stack, so we could rewrite it, right? So we save it on the stack, then once we have then our answer shows up in R1, and then R2 saves our answer before we pop. Okay, yeah, I see. Okay, great. So this looks a lot more like my function down here. And the only difference here is that there's this 8, this R8 happening where it should be 1. Is this saying R8 should be 1? No, not exactly. Because the result of this function should be 6. So R8 needs to be a value such that R1 equals 6. But hold on, this is just so weird because this is not, okay, this is a constant. This is a constant over here. Okay, so it's not exactly the Ackermann function. It just needs to be a value such that when we call it the 4 and 1, the result is 6. Am I winning? Hopefully, hopefully. I'm reverse engineering the Ackermann. So I have here for reference on the bottom left my a standard implementation of the Ackermann function, right? And here on the right, I am destructuring this bytecode. And I've got it narrowed down to this. This is what the bytecode looks like. So I've written in syntax similar to my own call. And the main difference here is that this case here has R8 as a constant instead of 1. And now we are expecting 4, 1 to be 6. So we have like an act 2, 4, 1 equals 6, right? And this is, what was that value? 65533. 65533. Because if you called that with a real Ackermann function, then it would give us 65533. Um, I don't think you're here, Bad Cup, when I mentioned. So I'm not going to do a compiler, but I want to implement the VM layer of the Jack VM. I want to implement that in Synacor instead of like the hack assembly it normally goes to, and that will allow me to compile Jack code and run that on Synacor. And I think that'll be a much much less daunting project than what you're doing. So we need this Act2, and it has a difference. There is a value of R8. And that value is used here as a constant. Now here's the thing. If this value is anything more than 1, okay, what happens in the Ackermann function? Um, we decrement m, and then we increment that 0, right? And then we're back to this case. So we decrement m, and then we do this. Eventually, eventually that m will hit 0, and we increment the right hand side. Let's just test out what happens with Act 2 with different values. So let's do Act 2. Act 2 of 1, 4. We'll try out some of these same values here. What we want is Act 2 4 1 equals 6. This needs an R8 value, so R8 is going to be 2. What happens when that's 2? Nothing changed whatsoever. And why is that? So we start with 1 and 4, go here, we end up with 0, and whatever the value is of AC 1 3, which is going to be 0. So that just unwinds all the way. Okay, so we never really hit this case here, do we? Right, so AC 1 4 is equal to AC 0, AC 1 3, which itself is equal to 0, AC 1 2. Oh, no, we did something wrong there. I'm going to make R8. Let's make that a, well, not yet. Okay. 0, AC 1 1, and 0, AC 0 1. Yeah, and we never ever hit this case. How do we end up hitting that case? The right-hand side needs to go to 0. Actually, we do hit it here. So this 1 on the right-hand side, X 0 1. Nope, we just never hit it. right? Because ac(0,1) just becomes n plus 1. Um, or 2 in this case. Well, okay, you know what? Let's fold this up a little bit. Let's fold this up a little bit. So we have that is 2. And when we have 0, 2, I'm not gonna I promise I'm not gonna run through any huge ones here. Not all who wander are lost. Indeed. High skill game. Welcome, welcome. Okay, and ac(0,2) expands much like this at the beginning. It's always going to be oh yeah. So that's going to be just 3 here. 3, and then this is going to be 4, and this can be 5. Hold up, hold up. Am I supposed to be calling it on one? Am I supposed to be calling on 1,4 rather than 4,1? Because 1,4 gives me 6. But if I do that, the value of R8 never mattered, right? Like this could be 200, right? If R8 is equal to 200, nothing changes here. Okay, wait, never mind. Never mind, maybe I'm wrong. But no, nowhere in here do we have the case ac something 0, right? If m is 1, we are never having... Is this m and n? This is m and n. R1 is m. So this is being called on 4,1. Yeah, it is 4,1. Totally. And yeah, and we know what the output value is supposed to be. The thing is, that's supposed to be that's what the output value is supposed to be. This is the output value we get, and we get that instead of that because of this. Okay, so at least in these cases here, in simple cases, we're never gonna hit R8. So let's do how do we get there? Let's just straight up do 1, 0 or something. So let's do Act 2, 1, 0, and for reference, we'll have Act 1, 0. And we'll set R8 equal to 2. Oops, just normal Act. Okay, yeah, stands to reason. Because we turned that to 0, and we hit the 0 case. So this becomes 0, 0, 1 versus 0, 2. And 0, 2 is going to end up as 3, as we saw happen here, right? Mm. And incrementing it even further is just going to increment that all the more. Okay. What if negative values, because this is pretty small here, right? Like, does it just decrement everything? So I want to see its impact on other things. So let's try Act 1, Act 2. And by negative values, I mean, we're going to treat the U15 space as assigned 14. um, because they kind of do that too here. Like something that will overflow to 6. Uh, okay, let's do 2. 2, and just good old-fashioned Ackermann on 2-0. 2-0, and why does this happen? So because it becomes AC1, right? AC1, and then that value. So that becomes AC1, 1, which then in turn becomes AC0, 2. The 2 side unwinds. Or no, AC0, AC0, and then 1, 2. Let that side unwind. But the result here is still just like incrementing it. Okay. Yeah, however much we increment this. So that increments it by 9. Right, so it'd be 11. Um, let's see. Let's do something like 3, 3. And with a normal value of 1. And then 3, 3 with a value of 11. That won't make it blow up, will it? Wait, I got the same value out of those. And why is that? Is it because of how big one is relative to the other? So let's do 3, 2, 3, 2. Wait, let's do AC. It's not going burr yet. I'm keeping it smaller than 4. Um, well, all right. Um, it doesn't matter. This is weird. This is weird, isn't it? Um, it doesn't matter what the value is of Act 2, or of R8 in this case, when we have 3, 2. It does still matter here. Weird. 3, 0? Okay, there it mattered. Okay, well, let's just do something similar to our end result. So we'll do 3, 1 instead of 4, 1. And are we still seeing a difference? We're still seeing a difference. Nope, we're not seeing a difference. Okay, you know what? I'm just going to straight up run it with 4, 1 and plug in different values. I'm not quite seeing patterns here, but it looks like these two have to be at least a certain number apart. It's hard to keep the stack frame in, in your head. All right, so let's run that with 4, 1. AC with 4, 1. AC2 with 4, 1, and 2. 4, 1, and 11. Let's look at those three cases. And in the meantime, while that's running, let's look at this. It's kind of like we are incrementing the right side more than intended. So in a case where this goes to 0, we were going to do +1, then we do plus whatever instead. Right, and in the case where this doesn't go to 0, then what happens here, R8, the right-hand side n, it increments that more than intended. Oh, was it not able to run that? Okay, we'll put Act 2 up in the console here. Okay, so Act 2, we want for 4, 1. 4, 1, and 1. That's just a normal. Excuse me. That's just a normal Ackermann. And then let's try it for 2. And then we'll try it for 11. We got the same value. That's not encouraging. Sheesh. All right. That tells me maybe I'm misunderstanding how R8 is actually used here. But we set R1 to R1 minus 1, and then R2 to the constant R8. Right, let's read this here. Add -1 to R1, and then set R2 to R8. A star? You're saying this is a search problem. But I'm saying I'm not seeing what difference the value of R8 makes. Is that a valid value? Oh, right. Is this a valid value? So, okay, these are ints. We're not anywhere close to some sort of overflow. 4, 1. Oh no, that's not a valid value. So that is that is, what was it? It's like it's FFFD. So it's not even a valid 15-bit. But, we could interpret that as 7FFFD or 7FFD. Right? Basically just truncate, I suppose. And we can just try that as a value for register 8. It doesn't hurt to do a little guess and check. It's just weird that register 8 never mattered, right? You call the Ackermann function, and then you check if its result is equal to 6. Now that could be like 6 mod the max value or something. Or actually, so this 6553 mod 0x7FFF. Oh, yeah. You've already tried that, actually. Shh. Negative? Do I need to try negative numbers? You know what? Let me see what the difference is with that. Oh. So 65533 mod that is yeah, sure. But that plus 6, no, E, F, that plus 1, that plus 2 is going to be 0. So that's essentially our negative 2. Um, hmm. It was expecting R1 to be R6. Um, so the reason I never came back to this right away is because things seem to work, right? Like I never actually set R8 to the correct value, but I do kind of bypass it by doing this. Um, I skipped this call and instead just set R1 to the expected value. But R8 is still used later on, and we did extract the function that uses it. Right. This function uses R8, 178b. Uh, oh, 178b is called in two different places. Oh, oh, what? There are two different calls to, oh, uh, yes, it's not called in two different places. That's a recursive call. Okay. 178b, I don't think it shows up anywhere in our stuff, but R8. Did R8 show up anywhere else? I'm gonna search here on the right side. R8. Um, how do you get that to equal 6? And is it an overflow? It doesn't seem to be an overflow because what this value um, is for one value. So let's just write that 0x FFFD. It is kind of negative 3. D, E, F, G plus 3 or plus 2. That would be the negative one, I suppose. And then, so that's the max value there. So plus 3 gets us to the 0. Um, okay, I'm gonna leave that up for a bit, go to the bathroom, and I'll be right back. Hmm. Okay, so let's step back into it. Uh, well, the core problem we're trying to solve is what value should R8 have? Um, and this function that uses R8 uses it as a constant value replacement for this 1 in the Ackermann function. Um, apparently, right? If my translation here is correct, then that is what it is there. And we see from the bytecode that it expects that after the Ackermann function runs, 178b, where is the call? Yeah, so it expects that after the Ackermann function is called, then R1, which I'm pretty sure is used as like the result of the Ackermann function. We can see that here by this push and pop. R1 stores the result of the call. That should be the value 6 after this is called. Oddly enough, coincidentally, Ackermann 4.1 gives us the value 6. Ackermann, or no, not Ackermann 4.1. Ackermann 1.4 coincidentally gives us the value 6. But we're passing 4.1 into here, and that gives us a very different value. Essentially like -3 in signed 16-bit. It's like a -3 short is what it is. Which is weird because that's much larger than our unsigned 15-bit. But I mean, even if we treat this as like an overflow, then what happens? We remove like the max. I think we still end up. We've just looped around like 4 more times or 3 more times, and we've still ended up with something that's not like 6, right? 6 does not look like an overflow of 65533, is what I'm trying to say there. Ice Cold Witch, welcome. And Paul Bardies, welcome. Synacor challenge. Here, I have a, oh, nope. Synacor. I have a summary there. But basically, you're given a binary for a foreign architecture and an architecture spec for that architecture. And once you get that VM running so you could run this binary, it turns out it's an adventure game. And to complete this adventure game, you need to reverse engineer the binary that it's running from. And at this point, the game expects a magic value to be set in register 8 when it runs the Ackermann function. It is used to replace this constant in the function, and the expected output when that function runs is 6. So when you run it with 4 and 1, we're supposed to get 6. The problem right now, the core problem right now is that I've made this implementation. This is what I think the VM is running. Replacing this constant doesn't seem to change the result, right? So is my Ackermann function even correct? Is this correct? Oh, fuck. Yeah. You know what? Let's go back to the Wikipedia page. I think maybe it's incorrect. So not equals 6 mod 16 is a register you were talking about. Um, not mod 16, but mod like the max. Yeah, if I were to run this version of the Ackermann function that I wrote, let me just plug that in. Let's Wolfram alpha, Wolfram alpha, Ackermann, 4 1. Is my Ackermann function correct? 65533. Okay, I'm pretty confident that's correct then. It'd be pretty hard to get that exact value with bugs. Okay, but the thing is, when I change this value, and it's not 1, and it's 2, or whatever is found in the R8 value, the result of Ackermann 4.1 doesn't change no matter what that is. But, you know, I don't know, let's make it 100. Let's make it negative numbers. Let's try negative numbers. So 4.1, let's try with -1 and -10. We're just going to run a lot of these. We're going to crash the stream. And let's run it here too. So when I mentioned 65533, you mean not yet. Am I doing my math in the same module as a VM? Well, you know what? I was kind of assuming I could just like overflow it afterwards, but I need to be doing that as we're going, don't I? Okay, all these plus ones and minus ones. What happens when you don't overflow as they should? Okay, we're going to define an ACLIT. A literal, yeah, let's do a literal translation of this. We'll see. We'll see shortly if it does matter. My instinct is that it doesn't, but like, you raise a good point. So ACLIT. So M and N are lits, and we don't have -1. So what we have to do is M plus 0x 7FFF. That's what's being used here, right? Yeah. M plus 0x 7FFF, N plus 0x 7xFFF, and all of those are going to be .2lit, 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 1.2lit, 1.2lit. Okay, so here's our ACLIT. And in fact, we'll even give it an R8. So these literals are unsigned 15-bit. And then this here. Yeah, all the literals in the VM are unsigned 15-bit. But the thing is, I don't know. FFFD, which is what this would translate. Wait, what? So I never overflowed 16 bits, right? So the result of the normal Ackermann function does fit in 16 bits, but it's not a valid 15-bit unsigned. And I stopped there because I didn't, like, this doesn't look like an overflow of that, right? Like, this wouldn't overflow to 6. So we're just going to make it that way all the way down. Case 0 dot, we'll do it this way. M if M equals 0.2lit. And we have an n here if n equals 0.2lit. And let's just indent this so it matches. If you look at the opcodes and consider how the ops are implemented, you get your answer. Yeah. Yeah, let me know if you want to see the spec or anything. And in here, my code is all up to date and cleaned up. So the spec is in there. The file int.scala has all the opcodes and its documentation. Oh, what happened with these runs? Probably nothing. So -10, yeah, even negative numbers, it doesn't matter what it is. I still don't completely understand that because sometimes it does matter. Sometimes it does make a difference what register 8 is. But for one in particular, it doesn't seem to matter. Right? Oh, these are all Act 2s. That's why that's not compiling. Uh yeah, we can let that run. But now I'm more interested in this. So let's get this compiling. We required an int. Oh, right, this is actlit that we're recursing with. Actlit and actlit. Okay. So this is a transliteration of our bytecode, which I'll leave on the right here. You can see past my head. Why am I saying it can't overflow into 6? I'm saying that because yeah, so it only goes it only increments by 1, right? Um I'm saying that this doesn't look like an overflow of 6 because it would be like mod 7FFF, right? Mod the max value. And in that case, it's like -3. I'm not saying that it can't overflow to 6. I'm saying that this value isn't an overflow, isn't an overflow of 6. Like this is more like, whoops, is more like a -3. Um, Unless I'm seeing that wrong. And if I am, absolutely call that out. Yeah. Okay, let's comment some of these out here. So let's play with actlit. So actlit, coincidentally, 1.4 gives us the value 6 that we want. But we want 4.1. What happens when you do this with just straight up literals? Oh wait, 4.2 lit, 1.2 lit. Okay, give that a second to run. Oh my god, did you figure something out? I mean, that's probably it. That's probably one of the first things I should have done, is literally translated it. This also needs an R8, so I'm gonna say R8 lit with a default value is gonna be 1.2 lit, and that can go into here. R8 32765. That is much better. Cool. So we actually have 0x 3, 2, 7, 6, 5. And what does that look like? Wait. No, not 0x. What does that look like in hex? So that 2 hex string, 7FFD. That looks kind of familiar. Oh, oh. Yeah, we've seen 32765 earlier. So my overflow calculation above was correct then. Um, yeah, so if we just take 32765 plus 0x, what's gonna be? Um, no. 8000. Yeah, yep. So the overflow didn't really matter. And it is still -3. So we can take that two binary string. I mean, we see the binary here. It's how many ones? So like it's 15 ones. Well, we can see that it's the width is 15, and then D, E, F. So -2, -1, or -3, -1, -2, -1, 0. Yeah, so it's still -3. Um, okay, so that didn't buy us anything but a little bit more confidence. So that's the int value, that's the lit value when we do it literally, or like more transliterated. And that's the two's complement interpretation. 101. Okay, thank you. Right, D is 1101. Cool. Um, okay, backing up again, backing up to the top. All right, we want to know what value of R8 we need. All we know is when Ackermann is called, we expect R1 to equal 6. So we need to find what value of R8 gives 6, but apparently changing R8 does nothing. It does nothing for values like this. For a value like, I don't know, 3, 3, 0, then yeah, there's a difference. There, we can do like 11.2 lit, and it'll increment that by 10. 20. So why does it matter there? Hard to say without expanding it. But certainly it's something similar to like why it matters in here. So in this case, it's going to be plus 10. Basically, when we have 0n, it becomes n plus 1, right? But we get to that 0, if we get to that 0n from here, then, and we add 10 here to this constant, then that's essentially like making it, just putting that plus 10 here. Oh, wait, here it didn't matter. Wait, what? Why not? Oh, no, we have to have 0 on the right-hand side for that to matter. And we get 0 on the right-hand side. To get 0 on the right-hand side, like, m needs to be bigger than n. I think. Yeah, the thing is, it does matter in a bunch of cases. It doesn't matter for 4-1. And why does it not matter for 4-1? It matters for 3-0. It matters for 3-1. Does it matter for 3-1? I think it doesn't matter for 3-1. Yeah. Because drop that. Yeah. I suppose, you know what? As long as that R8 isn't used elsewhere. The thing is, I think the R8 is used elsewhere. And we have a check for that. So in our VM state, we have this. We have a check for R8. And every time the string of an instruction has R8 in it, we mention and we print that instruction that used it. What are the values of ACLIT 411 and 412? They are the same, I think. Oh, you want ACLIT. Okay, let's do that. ACLIT. Bob, I assume you saw both Dave Eddy and Bad Cop finish up. So 411's a default 412.2 lit. Both yielded the same value, I think. And I don't know. Did I actually even try that? I'm actually I even tried that, to be honest. That's great. So you know what I'm missing here. I mean, as far as I can tell, the value of R8 doesn't matter in the vault puzzle. Unless it's just really obfuscated. So I could solve the vault puzzle independently before solving this. Um, yep, yep, same values. We can see it here. 32765. Which would be the -3 overflow. Okay. Well, let's look where else R8 is used. So Hackman, we set R1. Okay, 1592. R8 is accessed. We set R1 to the value of R8, which at this point is 64. Why is it 64? Oh, right, because we set it to some random value. Okay, let's switch gears for a second. We'll come back to this. But let's play our game. Let's play our game. Okay, so here's our save state when we start. So here's a shortcut to the teleporter. And what we do is we set the register to 100. That's the 64 that we're seeing. And then we use the teleporter. But also, when the Ackermann function is accessed, we skip over it. And we set the value in R1 to 6 to that expected value. Like, have I already solved this? Like, is there nothing else to solve here? Like not well, no, the value in the R8 should matter. And right now it apparently doesn't matter. Okay. So at 1592. So I accessed 1592 somewhere. In one of my worksheets. The play.scala 1592. No, let's go back to the scratch. 1592. Okay, here it is. Just full screen that. Okay. So R1 gets set to the value in R8. So this is where the value of R8 should matter, right? It's used in the Ackermann function. Oh, you know what? I don't know. What if it doesn't matter in the Ackermann function at all? No, no. Well, the Ackermann function isn't what tells us what its value should be, right? There still needs to be another check of the value of R8. And maybe reverse engineering the rest of this can tell us what R8 should be. Yeah, right? It's a hack that skips the Ackermann function. Um, so what's going on here? We set these three values. We have a -1. We have a magic value. And we save our 4 so that we can get another magic value. So we've got these two magic values, and we call 0731. 0731. And I believe I did extract that at some point. And I should have named my files more appropriately. Okay, so in our play, I think we do extract that, and if not, we'll extract it now. All right, we will extract 0731. No, we have extracted it. Yeah, we have extracted it. Oh, 0731. It's only called twice here. Okay. Well, let's run main Synacor dot play. Okay, 0731. That is this one here. Oh boy, that is a big one. All right, is used to compete the code that spits out. Fair enough, fair enough. Okay. So there's a call, there are two calls to 0731. And they both use R8. It's not used for the 6 code, I know that much. So, where's the other time that's called? So this call uses R8, R1. So the values here, we have R8, we have magic number, we have another magic number, and we have another magic number. Yeah. Well, Hackerman is the name of my skip, but yeah, I think I transliterated that wrong. We'll revisit that. We'll revisit that after this digression. Your sixth code is different for different R8s? Really? Okay, I'll have to take a look at that. I thought I'd verified it. Okay, so what I'm looking at here then, we have one call to 0731. I think there's another call to 0731. And it might just be a recursive call. Nope. It is called here. And with very different values much later on. Second call to 0731, different values. Okay, well, we can look at that later. We care more about this call here. So let's translate that. Um, 7 is 1. So we're clearing ourselves some space. We're going to overwrite R4, which is interesting because that was one of our parameters. So you push R4. I guess we still use that. We're just going to want to be able to overwrite to it later. I'm going to put this on the right side of the screen. So we have R7 equals 1, and we have R5 equals, well, we'll say R4, the previous value of R4 plus 1. And then we read mem. Oh, we read the value in R5 to R5, or the address at R5 becomes R5. Okay. What? So this is an address. So R7 is an address, and then we increment. No. I mean, this one, this arg4 is an address. We increment it by 1, and then we dereference it. Okay, R5 equals, how's it used in C? Star R5? Something like that. I'm gonna say, I'm gonna change, well, yeah. And then we add, so R6 equals, another magic number plus R7, which R7 was just 1, right? So that plus 1. Is that another address? Should we be extracting these functions? 07239, 07, or 7239. Okay. I don't need to, I spend a lot of time extracting these functions. I think I don't necessarily need to go too deep into this. We know R8 was used in R1, so let's just look around for where R1 gets used. Or rather, before this was called, R1 was set to the value of R8. Let me just double check that. So we have the call to 0731. It uses R8 and R1, as we can see here. Okay. And where does R1 matter? Okay, eventually we call a function, then we set R7 to the value of R1. We don't know if this function does anything with R1. And then we pop R1. Wait, first we push R1. Okay, we push R1, but we still have that R8 value when we call 084D. I think I want to extract that. Because that's really the only place this is used, right? So R1, so that becomes, it's saved as R7. We mod that, yada, 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 yada. And then we set R1 equal to that to call that. Okay, but we push first. Okay, so we use R1 as a parameter there, so that's not really using it again. Oh wait, we're pushing and popping R1. So that's because R1 is also the result of this function call. So function R1 is the result of this function call. R1, but it was still used here. Okay. So let's go extract that. Lower left here, we're going to extract a new function. Well, we skip that for now. 0x084d. 084d. Okay. Hey, that's not doing much. You know what? Let's just put that in here and indent. There we go. So we set R2 to the value of R7. Why did R7 matter? Wait, was R1 ever used here? So we AND R1. So this is the value that was set from the 8th register, right? We AND it with R2 to get R3. And then we NOT it. This is like a hash function of some sort. And then we invert it. And then we OR it with R2. Okay, so let's say it this way. So the result is going to be R1 and R3, where R1 is actually R1 or R2, where at this point R1 is the 8th register, okay, and R2 hasn't been set. Cool. And then R3 is going to be not whatever the previous value of R3 was, which is R1 and R2. And R1 is R8. Okay, this looks like something that should be familiar to me. We are XORing it. We are XORing it with R2, whatever R2 is. Um, or, and, not, and. Yeah. Oh, look. Copilot knows. Okay. So the only thing we do with that, then we save it to R7. So we XOR the value from R8. With R2, which at this point is something, is the other parameter. It's just that, right? R2 hasn't been used at this point. Cool. And then we push R2 before calling that so we could pop it back out. Great. And now R7 gets modded. So we XOR against R2, then we mod against R6, some value. Okay, so this must be the function that gives us our code, right? No? Is there any check? There's an equality check. What if I just hack this? R5, R6. We call this function. So jump faults to 075E. Where is that? Oh, that's a long ways away. Jump faults, R6. I think maybe we want this to be true. Jump if equal. So if this is true, then this shouldn't jump. And I guess this shouldn't jump. We could skip both of these checks. That might be one way around this. Push R1, set R1 to whatever that is. Call that. Okay. 05EE. 05EE. You know, I believe you. I believe you. I believe this bytecode has been cursed. That there's a lot going into that. Okay, so let's take a step back. We took a little digression, right? And we're looking for the other place where R8 was used. Why exactly? Just partially to confirm that does matter what we set it to. Maybe hoping to find a shortcut. But ultimately, we're doing that because we're not sure we've reverse engineered this Ackermann function correctly. Yeah, if you have the wrong inputs to the hash, you'll get a code, but not the right one. Yeah. Yeah, it's not like it's checking that you get the right code. And we're probably not going to figure out what R8 was by reversing the hash function. But that's what this whole thing looks like is a hash function. So this is probably what gets us our code. And yeah, for a hash function, like without the proper input, we're not going to get this thing to print out the correct code. But you know, I do wonder what these jumps are. I do wonder. Um, Great, but if that's the only other place it's really used, um, yeah, if that's the only other place it's really used, then I don't think I I I think we should focus back in on that Ackermann function. But now there's one thing I want to confirm before we get into that. So let's go into our game. And the Strange Book also does mention that a teleport is a validation check. It does, yeah. Okay, so I'm gonna not use a teleporter right away. Um, well, actually, right, we're gonna use the teleporter, and then after we use the teleporter, yeah, there's all of this north-south. We're going to the vault, so we don't want to go to the vault. Um, so we'll take all of that out and run main. Okay, so from here we can set R8 to 42. Oh, wait, really? Did I change my commands or something? That got passed along. Let's just get R8. Get R8. Did I change? Okay, it's very possible that I changed from one based to zero based, zero indexed. In which case, um, set R7 to 42. um, hold up, 1 second here. Register.from index. That gives us an ordinal. Yeah, you know what? We're gonna +1 this. This is the only place. This is the only place where that matters. The rest of the code doesn't do anything like that. um, that hasn't been affecting anything else. So that was an update I did before stream. I was just refactoring some stuff. Um, and yeah, let's set R8 to 42. No, no, hold on. Has no case with ordinal. 8. Okay, there's a get case. We fixed the get case. We need to fix the set case. And it should actually be -1 dot to int I -1. Um, and what's going on here? What is it not like there? Oh, wait. We need to do a to int bit. Oh, we never actually changed any code. So I dot to int, sure. I dot to int -1 there. -1. Okay, so from an actual index, I should just do it like from name. So reg.from string. Because my registers have those names there. Okay, so we'll set R8 to 42. Great. Now we use a teleporter. Um, and it was accessed there and used while making this code. Okay, so that code, TYEM, TYEM, nope, MD sum, sum, alrighty. Um, right, and I suppose maybe that didn't come through. 3130. Yeah, okay, right. So that one there is not correct, and that's when it happens when the code is generated. Um, and that means we need to go back. We need to go back to our Scratch 2. We need to reverse engineer this properly here. Okay, so here's the code. So let's check through each of these. Here's the first branch. This is the one that does not recurse. And basically, R1 is the output register, right? Before there's any recursive call, like here, we first push and pop. This one here also recurses, but I guess that doesn't matter because it's tail recursive. This one's tail recursive, so it does need to push and pop the variables. This one does need to push and pop um, R1. I don't know why it doesn't yet because it's setting R2 with the value from the recursive call. So it needs to push and pop R1. Okay, cool. So this is tail recursive. R1 is the output, and we add to R2 1, and we return that. Great. So when R1 is 0, we return R2 plus 1, right? That's pretty straightforward. I don't think that's wrong. Okay, so now we have this branch here. This jump of true keeps us out of this branch. So if R2 is non-zero, we're out of this branch. So we just have this. So R1 minus 1 and R2 set to R8. And then we call. So the recursive call with R1 minus 1 and R8. A tail recursive call. So that's pretty straightforward. I don't think that's incorrect, right? R1, R8. And then the third one here, this is the one that recurses. We have add R2 this, so we add minus 1. Wait, to R, oh wait, this is inside the recursive call here, right? So we subtract 1 from R2, and then we just pass along R1. And then we call. Cool. And we're pushing this R1 because we still want to use it in the left parameter. So after we call, we pop, and we add R1, this number, which is essentially negative. Okay. That makes sense, right? This looks correct. That is a proper translation of this bytecode. So then we go to our worksheet. And we look at our def ack. We look at our function here. We have +1, -1, and R8. And we have -1, and wait. Yeah. So m-1, this is like R1 -1. You know, we can rename these. Let's rename this to R1 so it looks similar. Oh no. Oops. What's going on here? I don't need that. In fact, I don't need any of that running because it's slow. Okay. So if we rename this right here to R1, we rename this to R2, then that looks identical, right? R1 -1, ack, R1, R2 -1. Cool. Rename this to R1. Rename this to R2. R2 +1, R1 -1, R8. Okay, this code is now exactly the same. And honestly, it probably has similar bytecode because this will have like the Taylor recursion optimization there. So if that is the implementation there, then why does changing R8 not matter given our parameters? And our parameters are 4 and 1. It does 4 and 1 and we expect 6. Like maybe I need to okay, are those parameters derived? Perhaps. No, they were constants. Were they not constants? So 178b. Yeah, we set it to 4 and 1. And we just run Ackerman. And that's the value we should get. I mean, do I just set R8 to this value? Well, what if I just do that? This is me giving up. I mean, if it's been that the whole time, it's been a number we've had the whole time. I don't know. Let's do it. Set R8 to that value. Use teleporter. Okay. And let's see, we sum. Wait, we have it here. Okay. Is that right? Okay, it's not that value. Good, like I don't expect it to be that value. Because that'd be weird. Um, so let's look, let's just expand this call to 4.1. And let's try to see why it doesn't matter what R8 is. Okay, so 4.1, this can be Ackerman of subtract the left, and then ack, keep the left at its original value. So we have 4 and 0, right? And the 0 is pretty easy to compute. That just goes out. So this is going to become -1, or a call to ACK -1. So this is 3. And then we have R8 right here. And a call like 3 R8 is going to have, it's going to expand to, well, I guess same kind of thing. So we're going to have, subtract this. So this is 2. And then recursive call with the original 3 parameter and R8 -1. Hold on, am I doing that right? So this Ackermann for 0 right here becomes Ackermann 3, 1, right? Or 3, 8 in this case. Ackermann 3, 8, like this Ackermann 4, 1, 3, 8 becomes 2 and a recursive call with 3, the same value. And then R8 -1. Okay, so like in the case of R8 equals 1, that immediately becomes 0. Right, and then that expands. But anyway, there are a bunch of calls, and every time that subtracts, well, the bigger this is, the more that should recurse. Right, so let's look at this for various values of R8. So if R8 equals 1 versus if R8 equals 2, we should see different things, right? So in this case, we have 0, and the 3, 0 expands to 2 R8, 2, 1, right? And then that 2, 1 expands to 1, and then ACK 2 and 1. Hold up. 2 and 1 -1. Which in this case is 0. And then the same kind of thing happens from above. But in this case here, so this becomes 3, 1. And 3, 1 becomes 2 and ACK 3. And 1 -1, ACK 3 and 0. You know what? I should just have a memo so that I do have like tables of this. But clearly, those values should be different. How about I do this with 2 different memos so I could see like what the values were, what the recursive values were. Let's start another worksheet. So this will be the Ackermann worksheet. Okay, so we have an applet. We really need to explore import numbers a star. Okay, we might need that. All right, so I think I've got a way to kind of figure out what's going on here. What I'm planning to do is have two versions of the Ackermann function, and we'll memorize them. And we'll run it on something like 4.1. And then we'll use that memo to see what the recursive values were returning and where it starts to differ. So Act 2, I'm going to have this defaulted to 2. So we're going to get a mutable map, memo and a memo2, val memo equals, oh wait, I need to import collection dot mutable dot memo dot map, sorry. Val memo equals map dot empty. Of 0 of int. And I guess we don't need to. We could seed that with some values, but I don't think we need to. So we have the mn. Oh, hold on. We want int memo int to an int. Okay. Lazy val calc was that, and then memo dot getter else update. Our key is mn, and our update would be that calculation. Great. I kind of worry. Well, no, I think we'll be fine there. And we'll just do some copy paste for a memo 2. Same thing, lazy val calc equals that. And we have the same memo.getterOuts update, but this can be with memo 2. Okay, so let's complete act for 4.1. And let's compute act 2 for 4.1. Now we're getting the same value, which is a problem. Wait, what's going on here? Stack Overflow error. What? That computed just fine the first time. Oh boy. Yeah. Okay, fine. This needs to be like a loop then. Wait, how is an overflow error when we were able to compute it just fine before? Right, we computed it fine just a second ago. Well, let's do it for small values then. 2.1. And act 2 for 2.1. That shouldn't be different. Memo dot size. We'll compare the size of these two first. Oh, interesting. Hold up, hold up. What's going on here? We have we're not using the same recursion. Here we go. Okay, let's try again. Okay, so Memo 2 has a different size, Act 2 has a different... Fuck me. Am I doing the same thing here? Um, Fuck me. Oh my god. This is such like a baseline stupid mistake. Um, okay, do y'all see just what just happened? Uh, so they're both calling the same function. Act 2 is not recursing on itself. Oh my god, how long? Uh, Act 2 is not recursing on itself, right? So that's why we're not seeing R8 have any impact. Yes, yeah, that's it. That's it right there. Oh my god. Oh. Wow, I mean, we went on a fun digression tangent there. We got to look at some bytecode and decompile it. That was fun, right? Um, wow. No one told me how long I was stumped by that. Jesus. Ah, oh my God. Um, okay, there has to be a way not to make this kind of mistake, right? I've done this before, and I've forgotten to change the name of a duplicate function. Okay, you know what? I'll think about that because that kind of mistake can cost a lot of time, and there has to be a really easy way to avoid it while still allowing me to copy paste everything all the time. Okay. um, yeah, like that can be a linter rule. It can be like, hey, that was intended to be recursive somehow. But that's it. That's it. So we can look. Let's see what happens. Let's do for 1 with a value like 1. Yeah. If we don't copy paste this, we're not going to see that in the first place. I mean, honestly, I should have just had. And you know what? We're not even passing along the R8 here. R8. Um, value. Yeah, we need to pass along the R8 value. R8. And here, R8. Okay. I can't ignore split infinitives. I've been too trained. Okay. Well, that's a relief. That's a huge relief. Um, that feels like a win. It's a win. It's me clawing back my time. So let's run a proper like Ackermann 2 then. You know what I'm gonna do? I'm just gonna paste right, so that should be that. This is my ACK. We'll call this ACK N, and we're gonna rename it this way. Rename symbol ACK2 to ACK N. That way we don't miss any renames. There we go. The actual ACK2 is just gonna be changing that because I want to paste that into a terminal and use it. And we could have an ACK11, right? There we go. Oh boy. We're about to make that same mistake. Okay. 11. Um, that has to be, if I could just peek at my am I being stupid list. Um, namespace collision. I think that falls under namespace collision. Yeah, I remember having an Advent of Code day like that where I just had for part two, right? Things were just copied and slapped a two on them. Okay. Okay. Like you certainly can just believe that's wrong and like keep taking a closer look at it. Um, I was exploring the output instead of exploring the implementation. Oh no, I'll think about that. So Act Two. Let's do Act Two with 4 and 1. Act 2. 4, 1. What happens? And an Act 11. Why not? Although I expect that to be like much larger. And now I have to look for something that, oh boy, that looks like a Stack Overflow. So changing it from 4, 1. Okay, well, let's do a 3, 1. We might have to turn this into like a while loop version. So let's just do an ACK of 3, 1. We expect 13. Nothing dramatic. Okay, great. Um, so now we want a value for 8, such that, well, let's have our act lit then, and we'll play with that. Um, yeah, we'll use this version. And in our recursive calls, we need to be passing along our R8, or else we're going to accidentally default to 1, which is why we didn't see the change in here either. And this is why I hesitate with default values. Okay, so here's an R8. And here's an R8. It's good for the UI, but not bad when you're like writing it. And here's an R8. And here's an R8. It's better to have like a given. In fact, like maybe I should make that a given. That's for sure automatically passed around. But anyway, that's done. We have an act lit. And we now just want to implement a fast version of this and brute force values of the register. I mean, like maybe we can math our way out of this, except the fact that it's probably an overflow makes that hard. No, we had a win. We had a small win. Um, we realized that cop is. Oh, okay. So remember here when I had my second version of Ackerman, and I was like, okay, this version of Ackerman, I set the register 8, right? And I was like, oh, okay, it's I'm not seeing any differences. I'm only sometimes seeing differences. I wasn't calling it. I wasn't recursing on itself. So ackn was calling ack at this point. So it was just calling the normal function, which is why I was getting the normal values. It makes perfect sense. It was a lack of debugging skills there, but we found it. So we found it. Ah, yes. Okay, so we can uh, mm, we can't do this actually, because I'm worried about stack overflowing once R8 gets marginally bigger. So we've got to do like a while loop version of this. Um, in which case, yeah, just comment this out for reference. We can comment that whole thing out. Um, actually, I think what I want to do is just do it with ints first. Nah, we're fine. We'll do it. We'll do it here. So we could do a loop while n is not equal to 0. So far, in fact, let's call them R1 and R2. So R1 equals m, var R2 equals n, and while R2 is not equal to 0, we do stuff. But after we do stuff, um, we have hit our base case. Um, and in our base case, we have just n plus 1. So what we return is R2 plus 1. You didn't hit any stack overflows using like full on recursion, even with oh, but where you're like memoizing. Oh, fair. I mean, I can increase my stack size, so I could do like SBT dash mem. Yeah, I don't know. Just give it. I can give it a much bigger. I can give it a much bigger stack size. I'm gonna do that. I'm gonna do that. Sure. Yeah, let's do that. Um, why don't we put this into a main file? Because I'm gonna run this via SBT, and I'm just gonna give it a lot more memory. There's no real reason to have this be interactive, right? So I'm gonna do act.scala. And before we do this, are we really just gonna brute force this? Like 4.1 already takes a hot minute to run. Um, right? And we're gonna do that with how many different values? 32,000, some values, 65,000. I'm not sure I want to brute force this actually. Not without an optimization. Hmm. I'm trying to think of like so my brain is right now is I'm trying to think of if there is any shared subproblems between the various values of R8. Right. I mean, certainly there's like some similar, like this line, that's not going to matter no matter what R8 is. And this line in the case where m is equal to 1, that's not going to matter because it's essentially just going straight to this case. I probably shouldn't try that. I could just YOLO let it run. And these are running on int anyway. And like perhaps if they are getting big, then like a memo does start to come into play. So where was I making a memo? Here. This. So we can make a map of lit to lit. Yeah, we'll do it. We'll do it. Lit to lit. The lits are secretly ints. And lazy valcal equals that. Indent that. Okay, and we have a memoized acclit. And we need a main def acc. Acc brute force. You assume based on Wikipedia that Ackman could not be mathed away. Oh, yeah. No, that's probably fair. Probably you do just have to brute force it. I wouldn't think that it can be mathed away. It can probably be Wolfram Alpha away. Except we have a variation of the Ackermann function. You know what? I wonder if we could use like a different representation of it. Like, what's this here? Ackermann's original 3-argument function is defined recursively as follows for non-negative integers m n 0 or m n and p. Of the various 2-argument versions, the one developed by Peter, so this is the one we're using here. This is called the Ackermann function by most authors. Can use up arrow notation. Okay, well, we're not looping. We're gonna make this recursive, and we're just gonna throw a huge stack size at it. So we have our thing here. Does the fact that we're starting at 4.1 give us any possible optimizations? The fact that we know that well, the tree can't be all that big. Excuse me. Yes. Yes, exactly that. And for various values of R8. So we can do iterator dot from 1. Let's do from 2. And we can do this as a for each. I think for each we need to make a new memo. So we'll clear the memo. Memo.clear. And then applet mn. And if that's 6, just do that. So if ands equals 6, then we're gonna show we can stop there. What do I actually want to do here, though? I think I want to show our progress as we're going. So we'll do like a line. So for each R8, yeah, applet mn R8, trying R8. Do we want to be print lining? Will that slow us down? Actually, you know what? Since I really want to, I'm gonna make this a while loop rather than using combinators here. Let's keep it a little bit raw because we might end up wanting to turn everything into while loops here eventually. So var ands equals applets, just a basic for 1. And while and is not equal to 6 mod, I guess and's mod, well, yeah, just 6.2 lit. Because if it overflows, it overflows. Okay, so we'll do a memo.clear. We'll show what we're trying to print. Trying R8 equals that, R8. And then we'll set ands to equal that new R8, and we keep going. And print line, R8 value found. Oh, where's our R8? We need to var R8 equals, we'll start with 2. R8 plus equals 1. And we try that out here. Okay. Found R8. And you know what? Why don't we print that result as well? Okay, that seems fine. Always some errors. 4.2 lit, 1.2 lit, .2 lit. R plus equals 1.2 lit. And M. Let's deal with M and N. Oh, this always gonna be 4 and 1. 4.2 lit and 1.2 lit. Okay. I don't check ends anymore. Yeah, I'm checking that it's not equal to 6. As long as it's not equal to 6, I keep giving it a new value. Okay. Okay, SBT mem. Free, 53 gigabytes. Okay. Why not? Is this the number of man SBT? Uh, SBT help mem. Oh, there's no mem in there. Okay, I'm pretty sure that number is like the number of megabytes. So mem 20 thousand megabytes, right? 20 gigs. You don't have to worry about Stack Overflow there. Nope, not there. And then run main Synacor.ac. Now, I'm still not super hopeful. We'll look at how fast it's proceeding. Run main Synacor.ac. Oh, there's no main def. Wait, package. Package Synacor. Yeah, there's no way I need that much, but I need more than whatever I had, and I know 20,000 is definitely more than whatever I had. Okay. Wait. Does that actually not update the stack size? Okay, let's ask ChatGPT. SBT run with bigger stack size for function calls. Post incrementing. All right, I'll display an off by value. Oh, okay. So I can't do mutation. I've been poisoned by FP. Wait, no, the value that we're trying is the same as the value that we're printing. Oh, right. But we're post incrementing here, so this R8 is going to be the wrong value. Good catch. Okay, we'll increment right at the start then. Uh, and we'll start that at 1. Good catch. um, XSS8M. That's the stack size per thread. Okay, I can just do that in my build options. Build.sbt. Scala C options. Or no, Java options rather. Or we do this. All right. Yeah, I'd rather do this. I don't want that in my build. This sets a stack size for SBT's JVMs, not a forked app, unless you already have fork equals true. I do have fork equals true. Right, fork. Yeah. Okay. This is what I was looking for here. We can copy and paste from the internet. And let's do more than 8 megabytes. I'll just add a 0. I mean, let's see. Like when I've done this, it means like a recursion depth of 1,000 if you're doing like factorial, right? Or something like that. Oh, run main Synacor.ac 17. Here we go. No, that's not a Stack Overflow. Is that Stack Overflow? I can't even see where the start of it is. Okay, like the bigger my stack is, the bigger the stack trace is. Um, okay, that's just telling me that a bigger stack size isn't the problem here, um, because it doesn't even print once, right? That's telling me that I have an infinite loop, an actual infinite loop. So let's look at this. What's going on here? Do we have a base case? We have a base case. Uh, if m equals 0.2 lit, are we actually hitting this base case? Is this thing happening? M is a lit, N is a lit. Hold up, hold up. 80 megs is a lot. Uh, how much is on a stack, right? This is 3 ints. Um, and an int's what, like 4? Uh, if each frame is, yeah, 80 megabytes is a lot. I don't even know how many, how deep my recursion depth should be with that. Um, let's call this with something really small. Let's just do 1, 1. Yeah, let's do 1, 1. And we should see it at least do some, right? And it's 17. Okay, yeah. Um, something weird's happening. Um, case mn if m equals 0 dot 2 lit, if n equals 0 dot 2 lit. Are these cases not even triggering? Right, like we can take out this whole while loop. Um, and we'll get the same result. SPT run main core dot. Here's a 16 megabytes. Good to know. What's the issue here? Unused local definition. Okay, sure. But that shouldn't fail my build here. So we'll run main synacor.ec. And yeah, sure, we did that. We can do a print line of ands. 4, 1. That should work, right? No, that fails it. Let's do 3, 1. And wait, no. Okay. Ran it, got 13. Okay. So no, that's not an infinite loop. That is actually a Stack Overflow. Um, I'm gonna set it. I'm telling ChatGPT here. I'm gonna set it in the CLI arg. And what is the default value? 8M is already. I know what I'm doing. Yeah. Um. most functional recursion is 4M. I don't. 1024K is the default. Okay, yeah, and I can recurse about like 1,000 times. Wait, no, that's still a kilobyte's still plenty. Um, that holds a lot of ton of ints. I mean, even the 8M should be enough. So there's no way. Look, I was just calculating 4.1 in the worksheet, right? I was calculating in the worksheet, no problem. I'm just gonna change these back to ints. And I'm gonna check if like modulo the value equals 6. Yeah, I'll do that instead. So we have a def ac. Is a stack restriction a JVM thing? No, nope. You'd have to have a stack size no matter what. My stack isn't restricted. My stack is huge. So I'm gonna take normal Ackerman. Here, we're gonna go with this. Ack run. We'll call this ack run. And we have no more Ackerman. Is it because I have the memo? Is the memo making it worse? Let me see. Let's just not use the memo. Let's make that full one. And was it not like? Yeah, it never gets reset, so they want you to make it mutable. Ack run. That is so weird. Yeah. Well, I only say that because this ran in the worksheet, right? Acklit ran in the worksheet just fine. 4.1. If I uncomment that, and I'm just reverting back to what I had here. But let's go with Ack. We can even memorize it. But we'll start baby steps. Do baby steps and make sure. Okay. So this we'll just call that function. So ack for 1. That should work. Hands down, right? Print line ack for 1. Yeah, whatever, you can skip that. This thing that runs just fine in my worksheet, right? We've definitely computed this value. Is overflowing. When I run it in SBT. I didn't even set it to anything. Like, what? Let's do 32. Okay, this time it did time out. Maybe, I don't know. Maybe they're like shared threads with like something running. No. Remember to do your +1 mod 32768. Sorry, what? Oh yes, yeah. I'm gonna do the modulo, but the end result, if you mod, so I was able to confirm that if you just modulo the end result, it's the same thing. So I can modulo the +1. I can modulo the end result. We'll get the same thing. Um, but yes, let's see that and 0x 7ff. Okay. Um, there's no bug in that, right? And I definitely did calculate that successfully, right? Okay, we can see it running here. Back 4.1's running here just fine. Back end 4.1.1 is running fine. We can try it with 2. See what happens there. We can try it, we can brute force it here in the worksheet. This one ran just fine. Um, something weirder is going on. There's no way. Worksheets always have the worst performance. Well, so here's part of the problem with the worksheets. The JVM instance that runs your IDE features, right? Like all of the hover, I don't know, type def, jump to definition, all that stuff. It's the same thing that runs the worksheets, right? So if your worksheet takes up the whole thread and blocks it, then your IDE can't run anymore. And I looked, and there's no way to give the worksheet a separate settings that I know of yet. Maybe I might have to like ask around a little bit. Um, this is definitely weird. So the issue isn't the issue isn't the code. We know the code works. We've seen it work elsewhere. It's just when it gets run here. Okay, this evaluation timed out, probably on that 413. Mm, what if we just start fresh and kill all Java, kill all -9 Java. Okay, let's go back here. And let's just do a straightforward Ackerman 4.1. Let that compile. And while that's going on, I'll get ready over here. Okay, wait, same thing. Okay, you know what? We're just gonna drop recursion altogether. Because the thing I don't want to do today is just debug JVM stuff. Um, yeah, let's do this as a loop. I started doing this as a loop somewhere. Yes, act.worksheet.sc. Yeah, I started doing it here. I didn't actually doing anything with it. So I'm gonna take r1 equals m R2 equals n. And, well, R2 is not equal to 0, do um, whatever. And eventually we just return R2 plus 1, and that is our result. So, well, we have to branch. We still have to branch recursively. Oh, hold up. Let's go back to the Wikipedia page because, okay, the Ackermann function specifically, you had to have done this recursively because it's a total computable function that is not primitive recursive. So this is a lost cause here. A primitive recursive function is, roughly speaking, a function that can be computed by a computer program whose loops are all for loops. Primitive recursive functions form a strict subset of those general recursive functions that are also total functions. Yeah, okay. So we can't do this with just for loops. It's not primitive recursive. We do have to use recursion. Am I understanding that right? I do have to use recursion to do this. And to use recursion, I do have to have a stack. I do have to have a stack depth longer than whatever I'm hitting here. Uh, does it tell me what my stack depth was? Um, oh, okay, you just need a literal stack. Sure. Sure, of course, that makes sense. Ah, of course, just any stack, of course. Perfect sense. Tomato, tomato. But you know what? I don't think that the value of R8 affects the vault. Um, I want to give myself a clean palette. It's 3 a.m. Let's go to the vault and let's give that a shot. I think I know what I want to do here. So we'll go. Um, okay. Play vault. If you allocate your own, you get to use a heap and you get way more space. Yeah, then I could just throw 20 gigs at it and go as far as I want. Yeah. But, I mean, way more space. I could just say stack size is equal to like 2000 or whatever, right? And that's still apparently not. I mean, I can make it 16 gigs, right? 16G. Can I do that? Exceeds the maximum representable size. Okay, okay. So there is a limit. But you know what? Let's see. 1024M. Can we do that? We could totally do that. My intent is still to go to the play vault because I have fresh ideas there. Um, Jeez, what's happening here? So we have this whole thing. This is our old implementation. We'll go with that. We are tearing up this file. It is a mess. Um, yeah, Applet does work. And 24 megabytes. Something weird is happening. There's no way. Yeah, I guess I could make it a while loop and put the stack in the heap, but that's still fishy. Maybe mmap the stack into the device and go wild. Why we don't need a big stack. We don't there's no way we need that big of a stack. Um Something weird is happening. And I think that's what the memo turned off. That's what the memo turned on. Same result. It should be able to do 4-1, right? Like the worksheet has a normal size stack and it can handle 4-1 with or without memo. So that main should also handle it with or without memo. Can you do memo on the big stack? Sure, I'll try that. Okay, that does it, right? Cool. No. Like, am I running code that I am running this code, right? I'm not running something that I'm not actually changing. Oh, and in here you could see the calls to the map, to the hash map. So we know it's changed. And yeah, the lazy function is proper stack too. So I think that kind of shrinks our stack depth. And if we were to do 4-1, let's do 1-1. Surely it can do, or 3-1. Surely it can do 3-1, right? Back run 3-1. No. 1-1. You can do 1-1. Something weird is happening. See, this isn't about stack size. This isn't about throwing more stack at it. Specifying the stack size on the command line only affecting the stack size. Maybe it's only affecting the stack size of VM running SBT. Even so, right? The fact that this here throws a stack overflow is an issue. It's like we're skipping this branch altogether. It's like we're skipping both these branches. It's like this guard is not happening. Let's change this to int. So, okay, we're just gonna place lit with int everywhere. 1.2 int still works. Oh, fuck. Yeah, you know what? It's silly, but it works. That should compile. Cool. And then now that that's there, we can just do this match here, right? We can match 0 and n equals 0 here. I just want to see this because it looks like that guard was not running at all, right? Our pattern match. No, that should absolutely be working. Yeah, I've broken something. Build.sbt. Did I do anything here? Nope. How's lit implemented? It's an opaque type on int, so it's literally just an int actually. So it should not give any performance cost. Numbers package. Yeah. Or hold on, it is. I think I was in the middle of moving it to a new file. What's ODA be called? u15.scala. So lit is a subtype of u15, which is just an int. And how the opaque type works is that in this file, where opaque is visible, then it is known that our value is actually an int. So we can use all the normal methods we would have on int. So I only implement the methods I want to use here. And for the address, I don't have math operations at all. So in a normal file, even though this is an int, in a normal file, I can't do addition with an address. So I only have these because these are the only operations I ever need to do with an address. Can we do some sanity check that we're running the function that we think we are? Um, well, here's kind of my sanity check is like copy paste this function. We copy paste this function and we run it in the worksheet and it works in the worksheet, or we run it up here, right? Um, let's see, we could replace ackint with play.worksheet, def ack. Okay, we have an ack that we know works, right? There's this one right here. So that runs in the worksheet. Let's just try ack here. Print line and let's just try ack here as well. So ack's the function that we're testing. Copy paste, run. Too many arguments. Yeah, we don't need an R8. And we got a stack overflow there. We got a warning for this being unused. Fine, fine. And if we do, let's paste it here, that same function. So we'll take this ack, paste it there, and let's run ack for 1. Interesting. So I've definitely run ack for 1 in this console before, right? You remember me running values? Because how did I get these values? I got these values here by running exactly that Ackermann function. I mean, I guess I could quit WSL altogether. Like, are we out of memory? We have tons of memory. I don't know what's going on. Yeah, my computer's broken. I mean, unless someone else wants to run. Like, what if I just can't run anything now anymore? Uh, oh no. Okay. Vault time. Let's do the vault. Okay, and my thought here was to stop using the lit in my state, use an actual int, and if we see that it overflows, we can worry about that when we get to it. If it gets to a case where it overflows, so we'll watch the values and make sure that that doesn't happen. But I also had a thought about like a potential optimization because if you look at our map, the most we can go down on any case is we can go down 18 at a time, right? So once we're at like 1,800, then, or like 1,830, then we're at least 100 steps away, or 100 times, 2, however many it takes to go down there. Because there's no divide, right? So my thought there is like you could use that actually for a heuristic function to prune, if that's even necessary. But basically, because of that, there's two implications here. One is we could have a heuristic function. Two is it probably doesn't get all that big because it takes a long time to go back down, right? We probably don't want to get too big. So like maybe I don't have to worry about overflow. And maybe it was wrong in the first place to use lit because then handling the negatives is a pain in the ass, right? So, um, Scala actually. Ackermann function works best in pen and paper. Yes. Uh, we just make an API call to Wolfram Alpha at this point. I mean, we never call it with more than, whatever. Whatever. So, lit, we're making this an int. And in this case here, none of that should change. This sub can just be weight minus n. And then we filter out negative. So weight starts, wait, what's this? Why was I doing 22? Oh, we start at 22. Right. Here's our end state that we're looking for. This is made like a Dijkstra. It's technically just BFS, but I'm gonna keep calling it a Dijkstra. And here. So in our state pruning, we check that the state doesn't already exist, because if the state exists, we already have a lower cost way to get there. And we want to check if not s.weight is less than 0. Or we could write it the same way we had it written up there, if s.weight is greater than 0. And I think our big issue here was that we just had too many states. So if we prune those states that get too big to get there in a reasonable amount of time, or if we could use that as a heuristic, what's the issue here? Not the overloaded methods. What's n? N's a lit. Right. Grid p.2 int.2 lit. That can just be an int. I'll just brute force R8 value instead. I mean, yeah, that's kind of what I was trying. I wanted to brute force it, but I don't know. 5 seconds times 32,000. It would have been a bad idea. I was trying to run it at least once, but we'll get back there. We'll get back there, and maybe taking a break from it and looking back at it, I'll have a fresh idea. So is this compiling? Sure. We don't care about this file altogether. Sure. Let's run that. Oh no, can we run this? Can we run anything now? So we're gonna run Synacor.volt. Okay, we're showing the depth. You can see it's slowing down in its cost. 17 steps. It's probably less than 100. I'm feeling like we do want to prune more though. Also, if I weren't print lining, this would be going far faster. The print line actually does slow down things a lot. But I want to see what's happening. So we are doing that. Some of those values are big. Okay, we are gonna be in the bathroom. Hey, I have a quick question. Um, so earlier I was running Ackerman with negative values, right? Uh, did we see the results of those? Did I actually? I think I started that thread and never let it go. So I want to look back at that. I guess the Volt just runs in background. Yeah, I think I wrote it, and then I must have commented it out at some point. So let's look at that. Because you want the value to be 6 from 4 and 1. Well, let's see. Yeah, I wrote some negative values. I never actually ran them. Let's see what happens when we have a negative value for R8. Right. I think we never even saw it because our R8 wasn't functioning properly, right? So if we comment this out, and let's just experiment. What happens when you make it negative? Uh, so ACK N, 3, 1. This is 13, right? When R8 equals 1. 3, 1, 1 is 13. Is it even possible given the initial call? Well, that's the thing. They're not actually going to be negative when they're lits. Oh, they would just turn into huge numbers. Hmm. Because we're unsigned. That was my thought with using negatives. Ah, okay, it's the same thing as just using a big number. Never mind. Never mind. It wouldn't make a difference. Um, I mean, hold on. Let's think about that. Uh, it still just checks if 0. And if this is not 0, it's going to increment it. Or, what's going to happen here? It's going to decrement it. Yeah, it's just going to throw us into here. Never mind. It's just going to be like using a big number. It makes no difference. Yeah, you're right. It only subtracts when the number is known to be positive. I thought around why negative would maybe be a thing is that okay, we're unsigned, so it's always gonna count as positive, and the function's still gonna work. I mean, what if we? I don't know. Okay, so back to the Volt. We have too many states, so we need to prune more aggressively. And are we actually seeing? Are we seeing duplicates? We're not seeing duplicates, right? We're not seeing much movement. A lot of the oh no, we are seeing movement. Right, our grid's very small. um, cool. We are seeing some huge numbers. And to get down to 30, I don't even know how you go. Like, what's our fastest negative path? Our fastest negative path, we could probably eyeball this. -8, -9, -8, -9. That's the fastest we can go down, right? -8, -9. So that's -27 in a space of 4. Um, so 7 per step, basically. We can go down 7 per step. So that is at least how many steps away? Um, yeah, I'm just going to add that here as a heuristic. That seems like a very straightforward improvement. Give me a sec here. Um, we search. Oh, hold on. One sec. Let me close the door. Uh, so to do a heuristic, let's do def h. Um, based on the weight. As a heuristic or as an extra node that just costs 4? No, no, not an extra node. So I'm thinking, yeah, I'm thinking about doing this as a heuristic. So for a state, and we need like a distance away that never underestimates. So it is at least that far away. So S is a state, and we have S dot weight minus N dot weight divided by 7. Right, let's do this equals, so it's minus 18, minus 3 minus 18, minus 3 minus 9. So, yeah, that's negative 27 in the space of 4. So we can just say 7 divided by 7. And that's like saying if it's 28, we're at least, if it's 28, we're going to say it's 4 steps away. Right, so even though it's 4 steps away at 27, so we are overestimating it, so that's fine. S dot weight minus N dot weight divided by 7. And we could add a constant, I suppose. So that we're definitely not overestimating. I mean, some of these are just so huge. I don't think that matters. I guess we don't even need to do this N dot weight. So we can just do, yeah, we can just do S dot weight divided by 7. Plus 100, why not? That's fine. That's never going to underestimate, but it will prune off those, or prevent us from going down those branches where the numbers get really huge. Okay. So we order by cost. Cost first. How do we fit in the H there? So by, so given the state, we have the cost of the state, plus the distance remaining. So if it's a low cost plus a high distance, then we don't want it, right? Plus, yeah, H of S. Cost gives us an int, right? What's the issue here? Ordering by, okay, let's give it type parameters. State and int. Okay. Let's try that. Okay, the numbers went up much faster. Seems like we're sticking around 20 for quite some time. Okay, are we seeing repeated states? And this weight is slowly getting bigger. I take weight, I divide it by 7 to get like the number of steps. It's at least that many steps away. Oh, I could still be underestimating the cost. No, 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 because that's the fastest way we could drop the weight, right? If that's the fastest way we can drop the weight. Yeah, that's not good. That is not good. So we're not finding paths that grow shorter and shorter. Or, yeah. Well, it isn't quite monotonically increasing, but yeah, generally it is. Um, I could add as a constant value like the Manhattan distance from the state to the end, and that would be accurate. Plus s dot dist or s dot pos dot dist to n dot pos, right? Not that it'd matter much because this thing is the weight here is the whole reason we're doing this. Okay, so we're not dropping in value. And in fact, we've already exceeded what we can do. So we need to we're overflowing, right? So 0x 7FFF 32,000. Yeah, we've overflowed a long time ago. If s dot weight, well, hold on. Hmm. Do those state values represent the current orb value? Yeah. So my state is the weight and position and the current operation, right? So what we could do, I could show how this grows. Maybe there's an issue in how this works. But basically we take our position, we take all the adjacents, right? And if we are already a constant, then adjacents are going to be these operators. And when you step on this pad, you're now about to subtract, add, or multiply, and it depends on what you get next. So now when you go again, you should get a constant. And you take that constant and you either multiply, add, or subtract. We could give an explicit north, south, east, west. If we took this and put it in, I don't know. Um, let's skip the search for a second, and let's have a start state. I'll start. We're gonna lift them both up here. We could parameterize search. We probably should start. And I just want to see what the states look like from here. I don't know if I actually ever confirmed. So, what if you enforce the limit not to exceed the max possible value? Yeah, I'm thinking about doing that. That will certainly make it shorter, but I fear what's going to happen is that it just ends the search right away. Um, so let me just verify our wait, what's going on here? Yeah. Start.next for each print line and start.next dot flat map next. Well, hold on. Not all of those are going to be valid, are they? Am I already filtering? I think I'm already filtering properly. Okay. Flat map next, and then for each print line. We need a dot next there. Okay, so here's our start state. From here, we can move to the right, and now we're subtracting. Wait, we start? We start with add? We should be starting with const. Or we could move up. Hold on, the first 4 points. Let me just get rid of this first. Unused local definition. Okay, yeah, there are only 2 valid places to go here. So we go to add, and then we go to sub, right? And our weight is still 22. And then after that, we do things that change our weight. Let's print some extra lines there so there's a gap. Interesting. Okay, well, anyway, these are our first 2. And now this one is the result of the add. We went north, right? So we went north, we added 4, our weight is 26. This one here, well, there's the, no, we didn't go north, we went east. Right. There is another one where you do go straight up north. 26. 1, 2. Wait. 0, 1. 1. Wait, these 2 points are 0, 2, and 1, 3. 0, 0, 2. Oh, it's from the top down. 0, 2, and 1, 3. Okay, 0, 2, and 1, 3 are here. And then we have a point at 1, 2. Here, we have 2 points at 1, 2, in fact. So one is 26, and the other is 18. So that is either -4 or +4. Okay, I mean, this seems to be working. All right, let's constrain it a bit. We'll just filter it. If s.weight is less than or equal to, and maybe we get rid of our heuristic function for now. So we'll comment that out. And we'll just order by cost. What we're doing before. Whoops. I don't think we need to have them both. S.weight is less than or equal to 0x7fff. That's our max value, right? 15 bits. Must be greater than 0, must be less than or equal to that value. All right. So let's run main. We'll turn our search back on. Okay, so this should die pretty quickly. Yeah, so it dies. So we were missing it. I don't think it's that our search is not efficient enough. I think we're probably just missing it altogether. Is our start state not... Do we actually start with 0 as a weight? So, like, do we have something that's, like, impossible to... Oh, right. Yeah, we can't do that. Starting at 22, that makes sense. R.main. Here we go. Okay, so let's... Oh, no. Let's go to our main file because we want the shortcut to the volt. Okay. Okay. 22 is carved into the orb's pedestal. Great. +22 +22 minus... Well, if you went up, down, right, left. That... I still don't know what the difference is between an orb shattering and an orb evaporating. It might just be 0 versus negative. North, south, east. Oh wait, we need to take orb. Take orb. North, south, east, west. Wait, we never took the orb. Take orb. North and south. Wait, north, south? Evaporate the pedestal right away? Maybe I'm misunderstanding this altogether. Take orb. So it's 22 right now. North. Okay, so we're on a plus. South. Interesting. Okay, I'm misunderstanding the problem then. So take... Because the same thing happens... 1 second, my thing's reloading here. Okay. Right, the same thing happens if I go east and then west. So we take orb, go east, go west. So -22 or +22 did that. Is this the register 8 anomaly? I think the anomaly is just the... It's just the reverse Ackermann function, right? North, north. There's the 4. So we've added 4. South, south. This should add 22. So maybe we do start at 0. Like, this is 22 if you were to go in here. So you can't enter this room, is that it? With a 0 orb. Well, if you did +4, +4, -4, -4, +22. That would fail us, right? Okay, let's try this. Let's start it then at 0. Let's start at 0. I'm doing this because north-south gives us that issue, and we can't enter it. We can't enter this room if we're 0. So we don't want to get rid of it just because it's 0. So s.current.next. Wait. Well, current is not equal to end. We do this. So we get all the next ones. And right, stepping north shouldn't cause an issue yet. So let's do that only when we're stepping on a number pad. Yeah. And s.op equals opcode.number. Well, this is an or actually. So we have a backup here, opcode.const. Or no, sorry. Op.const, right? Um, let's do that. No element removed from heap. We only ever got 2 states. Because we start from 0. When we land on a const, oh, right. We should run that first. But the s.wait should have changed at that point. When we call next, we do have updated wait, right? If we are in a const, oh, hold on. So if the grid floor is a const, right, that's actually when we're mul add or sub. So we want a not equal to const there. Okay. Nope. And you know what? That whole thing was silly. Like, one way I could have just tested that. Well, no, it wasn't that silly. So we are missing it. It doesn't seem like it needs to be that deep. What if we explicitly want an overflow? Hmm. That's a possibility. So why don't we do this? Well, multiply. Geez, what happens when you multiply? We need like double the number of bits. We could check. Our end condition could be if the weight is modulo. So let's see. Well, current dot pos is not equal to n dot pos, and current dot weight mod 0x755. Oh wait, am I doing that right? I'm just gonna mask it because I know that works for sure. 7 FFF is not equal to end dot weight. These values, this is like 26 moves before we've exhausted everything with any smaller values. Are we like subtracting properly? I mean, things go down, right? We did verify, right? We did look at a couple examples. We made sure it's able to subtract 22 and 9. That's what this code is here. Okay, current dot weight. And Boolean. I guess we need to print that is not equal to end dot weight. Okay, so this will handle overflows as well. Let's have a limit. Let's just have a higher limit. Yeah. Maybe it barely overflows a little. Huh. What happened here now? That's not weight greater than 0. Wait, oh, we start that at 22. I'm pretty sure it's 22. Well, no, I'm not pretty sure it's 22. Wait, what? Wait, what? What changed? We're at 30. How'd we get to 30? In apparently just 4 steps. That's fishy. What did I break? And then we have to print the path. Path to end. There's no path to the end. We didn't get to 30. But you know, we could at least print current at the end of that. Ended at current. There we go. No way. Okay, were we updating our path back, our parent? Oh, 30 at 1, 2. Right. This should be an or. We hit 30 in weight, but we didn't hit the top right room. Okay, there we go. Huh, there we go. It worked with some overflow. And 20 moves. That did work, right? So we ended at, so we're at the right position. 32798 is our value. Right. And now that 0x7FFF. Uh, and cool. Yeah. So we need to intentionally overflow. That's the trick. Or like, I don't know, like do this in lits. Okay, yeah, so we did need lits. But also, I guess here, after each of these steps, if I and accept the negative, that's a thing. The negative makes it tricky. I suppose I could just do it after multiplying. It's never going to be an issue for the others, right? So we do that, and 0x7FFF. Okay, now we can remove this nonsense. Do that. Cost for the current, yada yada. Okay, we still want weight less than or equal to that. In fact, we don't need that anymore, do we? So it's just weight equals 0. And we print the path at the end. And I think what we want actually is ands for each print line, so we can follow that path. And it's only 20 steps. Wait, no, what changed? Oh no. Um, okay, I'll keep this in here. I have no clue. Turned out weight and yeah, and a 0, 7. Must we do that for subtract too? I don't want to mask the negative number. Okay, well, if it ain't broke, don't fix it, right? I'm having the time of it. What happens if you don't do the masking? And yeah, it runs endlessly without the masking. Or, until we search our whole space and we cut it off. But yet, it never finds it. The only time we found it is when we have, I guess we don't need that either. This here. Where we check that our weight is some overflow of 30. So we will accept an overflow of 30, not just... Yep. Let's do that. And it wasn't that big. Turns out we didn't need to do any kind of fancy search. I can imagine plenty of people just got this on their first try. And then that state const. Okay, but how did we get there? State 30 point. Oh, no. We need to search from current. So you want path from current. Current.toList. And I guess we don't need to print everything anymore. Let's drop that print line because it costs time. Okay, so there's our thing. Oh, unfortunately, that's not very legible, is it? So I suppose we could get the points. We have to read up the directions from the points. Yeah, fine. Okay, that works. That works. Let's copy this down into here. And let's run synacor.main. Okay, we start at 0, 3, the lower left point. Right. And we go north to 0, 2. So wait. First we take the orb. Take orb. And then north. And then east. And then north. No, hold up. Um, North, east, and then more east is what we're seeing. Okay, left goes up, we go east. Right goes up, we go north. Um, and then we go south. So we're here. And then we go east. So we're here. And then we go north. I could have made it this easier for myself. And then we go west. This is our first west. This is our first west. Good. 270. And then we go south. We should hit a constant. Right. Because we subtracted 9, it got lighter. And then we go west. Fortunately, as I'm doing this, it is saving the history. Oh no, hold up. Your integrated rooms. No. We went west. From 2-1, we went to mole 1-1. That should be west. But we're seeing a mole. Maybe maybe the approach is to draw a path first. Let's draw the path. We'll draw the path and look at the. Okay. Luckily, we have an undo function in the thing, but also just drawing this out will help. So from here, we go north. So y diminishes, we go north. And then we go west. So we are now +4 to 26. And we go west again to sub. And then we go. Yes. North to const. 11, right? Yeah, we subtract 11. We're now 15. Then we go west. I should have modeled the thing that I'm saving as direction so I could build my path that way. Or like I could just store the direction just traveled. Would it, I think it'd be faster just to code this up than to do this by hand, but there's kind of a pleasure in doing it this way by hand. So we're now in a mole. In particular, we were 15. So we dropped to 15. And then we went right to the mole. And now we're going to go south to the constant. Huge constant. Yeah, 15 times 18. That should be 270, right? 5 times 8, 40. Okay, yeah. And then we go to the sub. And 2, 1. That's north to a constant. So minus 11. Cool. And then we multiply by going to the left to 1, 1. And then we go to 1, 2. No, let's not draw over that. We'll go to 1, 2. And then we'll go to 2, 2. So back to this minus. And we'll go to 2, 1 north. And then we'll go to 1, 1 again. So we are looping around. And then we'll go to 1, 2. Sorry, I hear chat, but I'm locked in. 1, 2. And then we go to 2, 2 again. Okay. Let's do it that far. And then from 2, 2 again, we go 2, 1, 1, 1. We go 2, 1. Then we go to 1, 1. And from here we go to 0, 1. Then we go to 0, 0, 1, 0, 0, 0, 1, 0. I already have an enum for my directions. I could totally just print the directions as I'm applying them. Like, but I don't know. I've started it. I want to draw it. I want to have the drawing at the end. um, so we're at 1, 0, and then we go to 2, 0, 3, 0. So 2, 0, 3, 0, and then back to 2, 0. We can do that. No, no, that's invalid. Oh no, that has to be invalid. Oh no. You were surprised when the solution was an odd number. Your solution was surprised when my solution's on an odd number of steps. Okay. Okay, nice try. Nice try. I see what you're doing. Uh, that's some great trolling. This though, this is surprising. I'm gonna run through it anyway. Um, but that's a bug. I didn't think. I thought I'd had that case handled. Now, all we need to do is. I was surprised when I said, "Please, no vault open." Mhm. Okay, here's an actual comment. I used to work at CWI. Then, when they spec'd out the requirement for new colloquium rooms, they insisted the number of rooms with chalkboards had to be greater than 0. Fair. I'll list numbers to mess with your counting. Did you actually do this with Google Sheets? Because that's not Bash. Were you running Bash in Google Sheets? Alrighty. Your friend found an optimal path by hand on the whiteboard in about 2 minutes. Really? Oh my god, it's one of those problems where probably should have just done it by hand. Working it out backwards, -1. I mean, that's the next step. If this doesn't work. Okay, I know I have an undo function. I'm not going to use it here. We're going to start fresh and see what's happening here. North. I'm not super hopeful because of that last bit. East. North. I do at least want to have this select in my save state or something. And east, south, west, north, west, south, east, north. Oh my god, that's a spiral. West, south. This should be my second time in the mold room. Yeah, south, second time in the 4 room. or third rather. East, north. And then west, west, north, west. Nope, nope, nope. That's east. 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 And it evaporates. What? Why didn't it evaporate? Okay. Great. Well, let's walk back west. I'm not holding an orb. Fuck. I'm typing this into a sheet, and it's going to become a shortcut. Okay. 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 One more time. You're getting tired, but you have to see do solve this. Well, you might at least see the vault opening. I feel hopeful. It seems pretty doable. The Ackerman, honestly, my best idea at the moment was to brute force it. But I can't even run it once right now while I have that Stack Overflow issue. So we'll at least get this. 22.03. Okay, so it's 0, 2, we go north. 1, 2, that is west. Oh, I'm already messing up. That's east. And there's autocomplete. Okay, you know what? Let's stop being silly. We're gonna print the path. Why don't we do this? We have a path. Path.zip, path.tail. Maybe I can't count, but I could at least code. Sometimes. And you know what? We can even make this inefficient. So what we're gonna do, we have an A, we have a B. We have an A and a B. We're gonna take all the directions. aoc.dir.values. Values. Okay. Valders equals aoc.dir dot. Oh, there it is. There it is. Okay. aoc.dir values. And we're gonna find the one that collect first or find. No. I guess we could filter. We're gonna collect first. So we're gonna collect first the if a dot move. So a should be a point. A dot pause. My path is a bunch of states, right? So case D if a dot pause. Oh, sorry. D. No, A here is a state. Let's. Before I do this, I'm just gonna get the. I'm just get the positions out here. So the positions, path.map, pause. We'll call it that, the pauses. Okay, and the pauses, and we zip that with its tail. Zip pauses dot tail. And these are points now, right? So we'll call them P and Q. Excuse me. And we're going to get the first direction such that P dot move self. That's how tired I am. Okay, so we take that path from current, move in D equals Q. Then we just give us D, and we get that. So val is going to be our directions, and I know just dirs up for each print line. Okay, minimal. I don't have to change anything here in my state. I can just collect it at the end. In case px, py, qx, qy. We can totally. Yeah, you can nest that. In this case, p is actually a whole point case class, so it'd actually be like x, y that way. So you can recurse as much as you want when you're deconstructing things. Okay, so now we're gonna run Synacor.bolt. That should give us our path. We still need to debug it, but hey, look at that. Oh, you know what? We wanna modify that a little bit. We want to print the whole name. There's up for each match. Okay. We don't have a. I was hoping it'd match exhaustive for us. So case dir.north. We should just import aoc.dirs actually. Import aoc.dir. And Copilot can autocomplete this. Copilot case. There we go. How does it get the path at the end? Well, so I did a search using a priority queue, sorting by the number of steps to get there, so that doesn't matter too much. But while I'm doing that, as I pop things out of the queue, or as I put things into the queue, I track the costs based on the current, and I track the parent, and then I just search backwards recursively. The priority queue is not necessary. I was gonna write a Dijkstra, and it turns out the cost between all the nodes are 1, so this is just a BFS with extra steps. But I wrote it and it's there, so I'm sticking with it. Okay, so here we have that. Now we could go to main and make that our shortcut after taking the orb. So what we can do here is comma separate these Wait, why did it work like that? Oh. Okay, comma separate those. We can just wrap that. Oh, you're memoizing it? You thought you could memo it, so you couldn't memo it. I think at least I'm onto something that the overflow might come into play. I don't know, suppose I just make my mole mask it down. I don't know what the behavior though is mm, if you modulo before multiplying versus after. I think it should be fine. So this I'm gonna call my take orb. Wait, what? How does it know? I must have take orb written elsewhere. All right. All right, it knows my pattern. And we can comment out this look here or delete it. Um, great. So let's just show up there. Uh, ROM hacking typically means like in a video game, you alter the game um, and make a variant of it by like taking the source and rewriting parts of it. So you like mod a game by messing with its compiled code and kind of reverse engineering how it works. Oh well, you write a new ROM. You make a copy of it. In this case, our memory actually is mutable, but we're not doing anything there. We're just extracting functions and injecting code at runtime. So, oh, that's the wrong thing. We want to run synacor.main. So I expect here, yeah, it seems like that failed. Um, if we take off the last few, so east, west, east, this one here, right? We can watch the orb melt before our hands. So at least we have our solution saved. We have a way to print out a new solution quickly. Um, look. Oh, what's going on? Okay, this happens sometimes with SBT. It's not my REPL, it's the fact that my REPL is running instead of another REPL. While that's happening, what we could do is look at Vault. You think BFS is optimal looking back? Probably, that makes sense. Why not just edit memory? There's no memory I really want to edit. So like I'm fine with injecting bike. Oh, right. Synacor is tricky, right? So I don't know, like I saw on Bad Cop stream when she edited memory to give herself items, um, they didn't work properly. So it's tracking your state. The memory's changing in really unpredictable ways. Um, so it's like taking some sort of hash of state regularly, or like how you got there matters. So, um, writing to memory is probably not the best, but injecting commands is probably safer. At this level, I'm just injecting full-on commands, so this isn't injecting bytecode, but I skip a validation check by injecting a command earlier here. So let's run this. Okay, so right now we are here, right? And then we go east, Wait, are we not holding? We went east. Minus symbol. We're staying. Wait, what? I think I forgot to get rid of some of my outputs when I did that. It's showing stale output. I don't really like how I designed my emulator layer, and I do have a big refactor I want to do to it, but that's, I don't know. I don't need a refactor to solve this. Right, the actual code doesn't exist anywhere. That makes sense. um, so we take or we progress until blocked, and we never removed the output queue. No, we progressed until blocked. Oh, we probably should still. So here's solve vault. I'm just gonna put take orb at the beginning of this. So take orb, comma. They all need new lines. Ooh, no, I add new lines. Progress until blocked, and then we feed the look. And I guess you don't need to progress till blocked twice. Okay. That should be fine. You can't cheat because the client doesn't send your score, it sends your solution, and the computer your score itself. Mm. Okay. So look, we can look inventory, east, west, east, east, west, east. Let's go back to vault here. Um, I thought I had it here. Nope, case. Oh, wait. I need to redo actually. It's too late now. Okay. I just want to make sure I have it copied somewhere. I forgot to copy it. Or rather, yeah, here's the raw output. And I'm gonna run through that one by one. State, and then we go in those directions to do that. And let's just delete some letters. Cool. And I guess at this point, at which point does it become too much, too big? 0, 0x7FFF, max value 32767. Okay, once we hit 32,800. So when we multiply by, I kind of wish I'd saved the consts in there so I could see what I'm multiplying by. But we could do that actually. So let's run to the vault. And I guess once we get here, we'll see that disappear, even though it's a multiply. North. Oh, wait. Oh, hold on. We have to stop the shortcut. So this shortcut here. Actually, you know what? We can look at how many of these points we need to remove. So there's all these easts. When we go north at 0, 0, we're at 4100. So let's go to that point. And at that point, whoop, at that point, we should have the orb, and we are in the top left corner, right? Ooh. Bad cop, you made a puzzle. Okay, I'm gonna have to look at this at some point. Um, so this is what was made at the jam. At, you are the algorithm. Compress text, repeat after me. All right. Okay, I'll look more at that later. But that's cool. It kind of gives me what's that Zectronics game where you kind of just run through, like, that has all the registers on screen. It reminds me of that kind of thing. This 100, yes. Okay, so here, look at our inventory. We can go east or south. So we're in the top left corner, lit orb and a lantern. And once we go to the west, so we are multiplying. Once we multiply by 8, it overflows, right? So let's go west, or no, sorry, east. The orb flashes yellow. The orb shatters. Okay, shatters meaning overflows. Okay, okay, cool. So that's important. So let's go to our pruning. So s dot weight needs to be less than or equal to 7FFF, and it needs to be greater than 0. Otherwise, I guess this is where we evaporate, and this is where we shatter, right? And in that case, if we can't overflow, then it's wrong to mask here. So we overflow, we're done. That's it. We go negative, we're done. That's it. Yeah. So now let's run the vault search again. No element to remove. Okay. Well, let's print and let's see what was happening before that. Right. No element to remove from stack. So I don't feel like it's an issue with my search strategy. Or, the fact that I'm doing BFS. I don't believe it's because of like overly duplicated states. Our pruning is fine. Our pruning's correct in at least this area here. Where else really are we pruning? We're making sure we don't have we're deduping state, and we're making sure we don't have those overflow cases. Great. Weight 22. Is my starting weight bad? No, it has to be 22, right? I guess there's still that question of why going north and then back south makes the orb disappear. That should add 22. Let's go back to main. Let's make sure I'm not imagining it. So we can skip these three here. Or, yeah. Alrighty. So we take the orb and you go north. It's a plus. It evaporates when we go south. I suppose maybe what that means, it means one of two things. It is 0 when we walk into the room, so that's an issue. Like it's still 0 from the start. Or it's 0 as a result of adding the 22. -9. +4 plus 22. -4 plus 4. No, -22. If I went north, north, south, south, I'm probably fine there. If I went -4, -22, that should get me back to 0. Big orb. North, north. Okay, it's heavier. South, and it gets heavier. East, north. Okay, it's slightly lighter. South. Oh wait, did I lose the orb? Oh, hold on. It's just every time you re-enter the room, regardless of what else happens beforehand. Okay, okay, okay. I misunderstood that. Well, let's go. Let's go here. And not pause equals n.pause. And not s.pause equals start.pause. And s equals start. Okay, same kind of idea. Well, all I've done is prune my search state even more. So at least I understand it better. That is almost certainly not the reason that we're failing to find it. Let's start putting this here on the right. Oh my god, it's nearly 5 a.m. I'm gonna take a quick bathroom break. I'm gonna come back and I'm gonna give this one more proper shot. Um, what's the idea here? What's missing? Could write some tests on the straight transitions, make sure that what we're making actually makes sense. I could actually just construct the expressions and then like evaluate them at the end. It seems like their search space isn't so huge that I have to worry about how format my representation is. But yeah, we'll think about that and debug this. Alrighty. Oh, water too, one sec. Um, so we're doing a breadth first search. Each of these is the result of some expression. Am I computing those expressions correctly? I think we are, and I think that because we've tried a few of these transformations and we can see it happening. Let's say I don't know, when we found a path, like this, 4100 multiplied to get 32,800. In that case, we were multiplying by 8. Yeah, we can already see that's correct. Okay, we're doing the expressions correctly when we move from state to state. Now, once we move the second time, that's when the weight changes, right? We feel that it's heavier. So this original state, we move north, we move east, and then the weight is 26. We're standing on a constant 4. Excuse me. Mm-hmm. Um, we tried adding this heuristic briefly to prune the number of states, but it turns out the game's required pruning of the orb weight, like it has to fit within the U15. So if it has to fit within U15, then we can search all the states apparently without too much difficulty. Um, I'm pretty sure these are valid expressions. Like we saw, for example, like we stepped from here to here, and the orb shattered. So it shattered, meaning it overflowed. Um, are we searching everything we can? I mean, from each position, we're going in all 4 directions. We're searching the whole state. Apparently, we've hit everything we can. Have we translated some of the state inaccurately? I doubt that. Yeah, we're pretty good. Hmm. Let's read the Fibonacci journal. Oh, my input seems broken. Oh, look at journal. Oh, I guess we skipped it. So south, south, and then we go east. Look journal. Alrighty. Hmm. It flashes colors, and sometimes symbols flash. It simply evaporates if you try to leave it, but neither appears on the pedestal. When the orb is carried to the vault door, the numbers in the door flash black. The orb evaporates. Heavier or lighter? Okay, changes weight, especially when you walk into, yeah, multiplying. Claim numbers in the door flash. Approach. Still didn't open. He noticed. What really gets me is that we haven't found even a suboptimal path. We are searching valid paths. Seems like they all get small. Or they get big pretty fast. Why isn't this path happening? Right? On any one of these like really long paths, you could at some point take a break and just go -9, -9, -9, right? You could repeatedly -9 or like -9, -18, right? So we should have an infinite number of paths to try. But I suppose maybe then it's the case that those have already been seen before and they've been rejected by the cache. Because we can get as small as we need to. Hmm. Okay. Let's look then at our cache. We're caching it by the state, and we're getting the cost by the state, right? And the state doesn't include the number of steps. The weight and the precision. I don't even need to Dijkstra this. But I do want to dedupe, don't I? Am I perhaps pruning too aggressively, and is it because of this? Mm, I mean, if it's on the order of 30-ish steps, I'll do a quick guess and check. Blinking a little faster than usual. The orb and me think, okay, flashes white, hourglass will run out, flashes black, and the orb evaporates. I mean, here's the thing. If we do hit a state, an identical precision, what is it? If we hit an identical precision and weight, and there is already a lower cost, then there's no point. We could just branch off from that lower cost, right? So I have to stand by this. I think I must be pruning true aggressively. I don't know. I could just try rewriting as a BFS and see if I notice something while I'm in the midst of that rewrite. Like sometimes that does it for me. Mm. Mm. And I could build the full expression at each step. Oh, you've done this before. um, yeah, I've been having a lot of fun too. Today's been a little bit of a stuck day though, on something that I thought I would solve last time, if I'm being honest. Um, let's step through this. We get all the next values, all the adjacent values. They're all gonna have a greater cost. We want to make sure we're not going negative or overflowing. Those are non-negotiable. And this contains is unimpeachable, right? The state is weight and point and precision. That fully determines that. If we can get to a weight and pause at a faster, at an earlier stage, then that's all the better because we can progress in the same way from there. Um, am I using the proper values? I think I've verified that. Yeah, I'm pretty sure I verified that in the Volt worksheet. Grid, 0.03, for example. Oh yeah, I've already done it there. Yeah, that's 22. I could play around and walk around here and make sure I don't see anything weird happening with my expressions. But I've already tested, and I'm pretty happy that my expressions are competing what they say they do. Okay, we'll take a shot at that by hand, see if we learn anything in the process trying to solve it that way. So 30 minus 1, like what if we were starting from the end? I can still undo all this yellow text. That was a dead end. So at any point, so if we can get 30 by here or here, we're also good, right? If we can get the, let's look at those. Well, let's start with the top, and we can prune stuff aggressively. So this is, if we were coming in from here, this is -1, right? So we have to have 31 here. How do we get here? It's always going to be by multiplying by 8 from here, so there's no way we got from here to there. Meanwhile, 11 times 8, no, 11 minus 8. Oh wait, something times, no, yeah, nothing times 8 is ever going to be 31. But something minus 8 could be 31. So this could have been a 39 here. 39 minus 11 minus 1. How do we get to a 39 here? Well, it's not going to be via multiplication. I mean, we could keep going back and forth between these two, certainly, right? It's like 39, what's next? 47. But if we keep doing that, then this is never going to, this x is never going to multiply to that, right? So at some point we have to go elsewhere. And that point might be like right here. So how did we get to 11? Or how did we get to 39? We could have subtracted 11 from anything else. Basically, we could only have gotten to 39 via subtraction. So from subtracting 47 here, from subtracting 47 here, that's an opportunity. That's more promising than this because of all those multiplies. Although, like, hold on, that's not, we subtracted 11. Okay, great. We subtracted 18 from something to get there, because we certainly didn't multiply to get there. Yeah, so plus 8, 55, 65. This could have been 65, 47. This could be 56. 56, 65. Okay. Now 56, that's maybe multiplied to 18 can get there. Hey, I'm liking this. Okay. 18 times, well, not 9. Or hold on, sorry. Um, something times 9 equals 56. So we had 8 times 9 equals 56, or 65, honestly. Okay, we can get there in two different ways. Well, it's not going to be 18 times 9. That's for sure. Well, the only other ways to get here then are something here. Well, we could add 9 to get 65 here, or... Well, we can't go into that room. We are doing... We're doing math here, so I'm backtracking from this 30 here. And I'm noticing some things as I'm doing this, right? So there are a lot of branches that disappear altogether, just by virtue of the fact that like multiplying there doesn't work, right? So I can't have gotten to, let's say if my end solution was 31 into there, I can't have gotten to 31 by multiplying. So these branches are dead. So the only way I could have gotten there is via a minus here. There's only one plus. That's interesting. Yeah. And I'm kind of noticing like we could do some sort of node compression of some sort. Like this here never really matters anymore. It's just redundant. This plus. Okay. I want to backtrack on this one a bit. Did we already get with code? No, we didn't. Our search terminates And I can pull up the code if you wanna see. Like, here's a state transition. I'm pretty confident about the state transition. And here's my pruning. And this oh, prevents evap, prevents shatter, right? Like, I have evidence that both of those are necessary. And then this deduping is necessary. Prevents suboptimal. And apparently that's too much pruning, and I run out of states. The same bug as you somehow. Well, I know at least the math was computing, like all the way up to here. I think it needs to be greater than 0. The last operate, the +1. It wouldn't do that for me. Like, as I step into there, it does it. And we have a trace of 1 that thought it was correct. So here we go east into the room, into the vault room, and that should be subtract 1, right? The vault room is 1. So there, that last op is working for sure. Um, we can verify like this by hand, right? Like 22 uh plus, oh, I don't know what the constant were in there. I can print that again with the actual values of the constants. But yeah, I'm perplexed. So while I'm hoping that solving it a little bit by hand helps me gain some insight, or helps me come up with new ideas. Um, yeah, I don't think that's ever going to be that way. Let's think about the multiplication here. So, can you ever get? Would it ever be the case that the last step that there is north, right? So multiply by 1. So that means at this point we were already 30, and that means to get here we were either 31 while standing over here. Well, hold on. So we are 30 from here, or 30 from here. And multiply by 1. So let's look at this. Let's look at this branch down here, 30. How did we get to 18 and be 30? Well, it's not from the north because nothing multiplies by 18 to get 30. It's not from the south. So those are impossible. So it has to be from here, right? So the ways we get there are 18. So minus 18 gets to 30. So we add 18. So 58. 58 from here, from any of these 3. Right? So we had 58 minus 18 equals 30 times 1 equals 30. Okay, so if we can get to any of these states, 58 at that position, 58 is unfortunately not a multiple of 4, but I'd like to use that times 4. Hey, didn't we have a 56 here earlier? Okay. Evaporates if you touch 0. What one thing I wasn't realizing for a while is it evaporates if you go into the start room, regardless of what its weight is. I didn't catch on to that. So we're not about to return back here. What does line 61 do? Hmm. So that checks my cost map, right? So that's the number of steps to get to that state. So the number of steps to get to the start state was 0. And since I'm doing this in a priority queue based on the cost, that will always be the lowest cost to get to that state, right? Um, yeah. It's not even really a heuristic function. It's just like the maximum is like the best. It's a min cost path to get there so far. And there's no way, any other path that gets there is going to be greater because we're doing a Dijkstra. I could just uncomment that, see what happens. So remains Synacor.volt, but we should have like an explosion of states. I don't know. Maybe it's not that many states. Maybe the other pruning makes it better now. Cost is just a number of steps. Yeah, so this is just BFS. I mean, I could add plus Manhattan distance to the top right as a heuristic function. Oh, but I mean that's not even going to be necessarily. We're seeing quite a variety actually of weights. Oh, right. Yeah, we're seeing like infinite loops and stuff. um, yeah, there's no pruning at all. So we're revisiting states over and over again. But yeah. Um, solution at depth 14, really? Well, I mean, I'm pretty sure I've hit everything at depth 14. That's not a troll because it was just on 14, is it? I can let that run. Like maybe there's one that I accidentally pruned somehow. But if I prune it, it's because that state was already reached in fewer steps. Great. Well, I mean, I don't really even need to dedupe. I can just let it run. Yeah, Zuno, I tried. Thanks for sticking around. At 14, you found a bunch? Cool. Well, it's like 8 steps to get there. At 14, I could do that by hand. Maybe it's not printing out the valid ones. Like maybe my end function is not working. Well, okay. Let's look at this. This is the end state, right? 0, 1, 2, 3. Actually, we've seen that this end state appears. Well, it does stop, right? So this is a case where it stopped when it found that, which was two kinds of wrong. It's wrong because the overflow here breaks it, and two, what I did here was like I modded it. So this is 30 mod max lit value. So that case, if we allowed overflowing, like this is a solution. Oh, but the other issue is also like it walks into the end room and back out and then back in. Which, did I fix that? I see. I suppose I could just write up another solution, do a DFS. Like, I'm sure it's just some silly bug. It's not like this is a hard thing. I left him out in the car, but I'm regretting that because um, lights get to me after a while. But hey, how you doing? Yeah, it looks like it should work. I know. It's nice just but the night like staring code that should work, but it doesn't. My Ackermann function overflowing at 1-1. Um, but Dev 14, we can do this by hand. But this has now become a math stream. I need to change categories. Um, how do you get to 4? So these things are multiples of 4. Um, I think we need to get both 22 and 18 together in order to have this top left be relevant at all, right? Or no, I'm thinking about it backwards. So if we're multiplying to get to 58, yeah, we need to hit 18 first. Or we need to avoid hitting 18 in the first place, actually. Mm. I haven't been reading the code the whole time, but I think your implementation is close to mine. Throw Manhattan distance in there like you already suggested. Yeah, I might as well. Did you get this, Bob? Excuse me. Okay, def H. State. Oh, wow. It auto-completed to Manhattan distance. It knows I want to do that. And that should be right. Oh, look, we're up to 15. We never found it. Okay. Um, Yeah, I've never seen Bad Cop doing leak code. Okay, there's Manhattan distance in there. Oh, did I return this? Some of these are actually many steps. What's changed? Oh, right. What's changed is that the Manhattan distance thing is allowing these to be prioritized. Sure. Let's do that. Let's turn that back on. We still end up running through the whole queue, right? So this would just change the order in which we pop things from the queue. Yeah. Well, I over-engineered a Dijkstra when all we needed is BFS, so I wouldn't hire me either. And I've been staring at the same code. Um, all right. Back to the whiteboard a little bit. So 30, we get here from like a 58 here. How do we get to 58 here? Minus 11 from something odd. This can't be odd though. So this here is a dead end. Unless it's minus 1. Nope, it can't be that either. Was it multiplying? We didn't get to 58 by multiplying. We didn't get to it by subtracting. Unless there's like a lot of back and forth. Ain't that the truth? Depth limited DFS with increasing depth is basically, yeah, true. Yeah, you're basically doing BFS. Okay, so I'm gonna abandon this branch here. How do we get to 58 from here? Well, we could have added 4 to 54. 54 could have come from here, right? But that's it's not a multiple of 8, so that wouldn't have come from here. There's all this back and forth. Oh, holy shit. 22, we can just keep going up and yeah. Wow. Oh my god, I was right there the whole time. 22. 26. Yeah, I've got a solution. Is right in front of my face. So 26, and then from 26, 30, 34, 38, uh, 42. I can't math. 46, 50, 54. Ah, no. 58. 54. Am I mathing that right? Oh, no. We just start in the opposite direction. So, oh, I've got it. I've got a solution. Okay. All right. All right. So, we've got this. We go right first. Um, so this is 26. Wait, you found it manually? Oh, is it not optimal? Okay, it's a solution, and why can't my search find it? Okay, yeah, it's too slow, isn't it? What if we put in a times 4? No. Okay, fine. Do we have the same grid? We have the same grid. Yeah, I'm gonna try it. That will be information. Um, okay, so 26, and we going back and forth. Let's give ourselves more room. Mm. You know what? Um, I should just condense my nodes altogether when I'm doing my search. I don't need to like simulate a full grid because we just need to search like expressions, and from each you have several. I might do that actually when I re-implement this as a BFS. So 26, 30, 34, 38, 42, 46. 50, 54, and 58. So a bunch of back and forth. And then minus 18 gets us to 30 times 1 keeps us at 30, and we're there. So how many times is that? 1, 2, 3, 4. 4 visits to that room, which means that's 8 right there. 1, 2, 3, 4, 5. 8 plus 5, 13. That's not bad. Yeah. Okay. So let's type that path in. So we'll go to main and we'll stop here. So we'll have a new solve volt. Take orb. And we go north, east. Then from here we go west, north. There's 1. South, east. Okay, so there's 1 loop, right? West, north, south, east. And we do that 4 more times. So 1, 2, 3, 4. And then from here, we go east, east, north. And I'm going to stop there. You can totally get up and try it, or you can bring your laptop into bed. um, by the way, I got an ARM laptop. I won't use MacBooks. I wouldn't get the M1. But I got an ARM ThinkPad, and it's so like light and nice, and it runs cool in bed. So like I'll bring it into bed and watch Twitch and start coding, and it'll be like 5 a.m. It's bad. My normal laptop I work with is a big old workstation, so it's not really portable. Oh, these days I run Windows and WSL. So same system I'm running here. But I don't know, like Arch compiles to ARM just fine. I was an Arch user for a decade. Okay, from here we go north. You stand before the door to the vault. It has a large 30 carved into it. There's a running hourglass which never seems to. Wait, okay. As you enter the room, the orb briefly flashes yellow. The number on the floor vibrates beneath your feet. As you approach the vault door, the number on the floor on the vault door flashes back. The orb evaporates out of your hands. Okay, cool. Well, we've seen that happen. So that's a solution. And as for like why my code can't find that solution, good question. Well, like we know it's solvable. Why WSL over Arch? Initially when WSL1 came out, and I heard about its architecture, I was like, oh, that's cool. So, I started dual booting, and I gave it a shot. I was like, cool. Well, you can do stuff. And that was in like what 2017 or 2018. Um, and I didn't jump there yet. But then now I had like a laptop with a discrete graphics, and I was like, oh, I can play games every now and then. Um, I didn't want to do multi-lib on my system, So I was like, okay, well, let's just do. And they still don't have a 64, 32-bit launcher for Steam these days, I think. So I go to Steam. I go to Windows every now and then for Steam. And when I go back, I go check out WSL, whatever updates are there. And I was like, oh, this is actually pretty usable. Um, and I think part of what got me, there was some sort of lock-in. So part of the lock-in right now for my stream, my equipment and my software doesn't run on Linux. So like my Elgato software doesn't run on Linux. Um, I don't know. I think I started using it for work at some point. Or maybe I just like the pandemic hit, I started gaming a lot, and I was like, okay, let's just start doing stuff in Windows. um, I don't know. The thing is, like, I put my dot files in, it just works. Um, yeah. And at some point well, I think before even there was WSLG, you could run an X server in Windows. Put in my dot files, everything just works. And there's a trade-off. There's a trade-off in like the kinds of like you don't have the same control over your system. Uh, you don't have the same ability to debug it when something goes wrong, but also like you don't have to debug your Bluetooth as often, you know? Yeah, I can't remember the story exactly, but just slowly sucked me in. And I was like, okay, I can have the best of all worlds. I can like play my video games and run this software. Um, you went from WSL to Arch only. I mean, I get it. Using Arch is nice. The thing I really hate about WSL, well, I'm using Ubuntu in WSL, and I hate not having the rolling release. Like often, versions are behind, and then like I might have to like build something or like download it from like an alternative package manager or something like that, and it's nonsense. I want to just be able to, you know, get the latest from Pac-Man. But yeah, why isn't this finding that? Let's go to the vault. WSL prolonged your transition to Arch. So you went back in that direction too. Do I use a do you see use any AV on Windows? What do you mean AV? Like audio video? Like I do all my stream stuff on Windows. Um, it's easier to do there. When I first started, I tried streaming on both Arch and Windows, and I didn't have like the same integrations. Um, and I was getting better performance on Windows too because of the NVIDIA graphics card or something like that. Mice, okay. I mean, it's not enough of a problem. Like it's a minor annoyance. But you know, Windows Terminal is actually good. Um, yeah, and like things have been getting nicer. Like I still feel like I have a decent Linux experience. Like the Windows tiling management is good, or you know, at the very least usable. It's usable for me in a way that like the Mac OS tiling management is not usable. Yeah, I used to do like run Arch and Xmonad. Da. So How could we verify that it's search? Like, what happens in the search space for this? Um, why does this get pruned, basically? How many steps is this? So this is 8 steps just here. No, no, no. This is 8 times 4. No, no. We bumped from 4 to 4 4 times, right? That's 16 steps right there. 16, 17, 18, 19, 20, 21, 22. That's 22. When we do this full search, we hit the end at 25. There's never 22. But we could look through all of these states. Here, what I'm going to do is run a new terminal. So I can just search the entire history. And we'll SBT. Oh, is it going to complain I'm running multiple instances? And we'll run Synacor.vault, and we can search for history length was bigger here. Do I play D&D? I have played D&D. I've never finished a campaign. I'd like to try more. But why do you ask? I know the basics. I've switched back and forth between Debian and Ubuntu, and sometimes I have multiple WSL instances. Okay, it gets pretty big pretty fast. Let's do the initial search. I should just DFS it so it's like scrutinable. Scrutable. Okay, now can I find it? State 58. After 9 steps. Because from there, we're about to add. I guess there's a times 4 or something. Let's try something new. So let's copy and paste. You know what? I've got this path memorized. I'm just going to delete it. Undo that. Okay. So we can do a 22 plus 4 times 4. No, what if we did a minus 4? Minus 4 times 4. So 22, 18, 16 times 4 is 64. Well, let's see. How about 12 times 4? 12 times 4 is 48. Nope. That's the wrong parity there. But yeah, we could do a circle around. That's 64. That's 68. My circle was too good. We can go to 59. I'm trying to avoid odd numbers, to be honest. Now we're off by mod 2, so like 4. Yeah, I went from WSL to from Arch to WSL. I also went from Emacs to VS Code. uh, so I've abandoned all of the. Next, I'm gonna go from Scala to Java. Hold on, I'm missing your chats. Do I like a Star Wars D&D theme? You ask because you're curious. Would a Star Wars Evil D&D campaign maybe interest you to join? Um, Maybe, maybe. Okay, yeah, reach out to me, like on Discord or DMs here, and that could be fun. You tried out BFS and it works. Great. So 16 times 4, 64. We can do as many of these subtractions as we want. So 64, 68. I suppose we could always add 4 first. We could end up with any multiple of 4 here that we want, or any multiple of 2 mod 4, basically. So 26. No, you know what? I missed math there. I think I was telling lies. So 22, 18. This goes on to 14. Okay, right. So 14 times 4 is going to be 56. It's not a bad number. And we can do 60. Let's see. Earlier when we went to 58, we zipped between these two, starting first to the right. Right? 26. Um, so if we go here and you start with 18, well, if you go up the top, we can start with 26. Well, it's kind of the same parity, right? I can go up there, I can go down. From here, we still go back up to 22 and up to 26, and then do the same thing. So we can find less optimal solutions there. Um, but a multiplication times 4. So 14 times 4 is going to be 56. Now the parity is different. Anytime we do this, multiply by 4, we're going to take the times 2 part. We're going to switch to parity of our 2 mod 4. Yeah, once we do that, we are in multiple of 4 land. And no matter how many times we do all this stuff, we're gonna remain in multiple of 4 instead of 2 mod 4. Okay. Do we want to be in multiple of 4 land? I don't think we do. Because is there a multiple of 4 away from this 30? Well, I mean, if we were subtracting an 18, 30 plus 18, 30 is 2 mod 4. 18, how did we get actually 58? Next one, 30, 30. 30 times 1 goes there, right? Minus 18, 58 minus 18. Uh, it surprised me a little that 58 and 30 are both 2 mod 4, but I suppose we subtract, yeah, we're subtracting 2 mod 4, and it's still 2 mod 4. Why? Fuck, it's 48. It's not 58. Oh, wait, did the thing we ran even flash correctly? I didn't actually have a solution. This is 48 here. I can't, I'm not mathing. All right. So let's go here. Okay, handwritten solution here. I've got this. Uh, so we could hit 48. I think I'm most interested in this branch right here with the 4, 48. That is a multiple of 4. Yeah, so this is 2 mod 4, this is 4 mod 4. So that came from 12 times 4. So we can get here, it was 12. Boop, boop. This is 12. Can we get to 12 there? 22. By adding and subtracting 4s, we cannot get to 12. Right. We can get to 18. And then we can go further down to 14. So that's maybe a dead end. But what if we subtracted 9 twice? Well, okay, that's an 18. 48 minus 9 minus 9. Or, yeah, that gets me a 30 here. Or minus 9 minus 18. Yeah, we can do as many of these as we want. So 18 is twice that. Yeah, absolutely. Yeah, thanks for letting me know about that. With yours, okay, let me catch up here. With yours, you suspect that this is a side effect of the order in which we are checked, not representative of the algo's general. Okay. Mm, At least we have an upper bound. I don't know why it's not found here. I think our termination condition is okay, right? We've hit our termination condition before. Well, ish. Like, oh yes, asking absolutely to you, the known dark senate. Okay. Maybe. It'll depend on work hours with my upcoming client. So, not sure how much I can commit there. But being in the loop at least would be nice. Okay, so we're not going to get to a 12. Um, unless we like got some big number and then subtracted multiple nines. No, 2 9s. Yeah, we can always subtract an 18. What if from 48 it could be 52 if we came from here. 52 minus 4 to 48. Okay, 11. How did we get to 11? This could also be times 4 situation. Oh, no, times 11 situation. There's no times 11 that gets to 48. So that's not an option. But there's a times 11 from 44. Can we get there with 44? So 32. Okay, this is subtracting 18. Oh, from here, from 48, we go up here. So 52 minus, oh, no. 52 minus 4 got us to 48. And then 52 minus 4 gets us to 48. Yeah, no, we were hoping for 44 there. If we're ever going to use the times 11 route, we would need like a plus. So anyway, this to the left of this 48 is dead. Did we come from up here? So if we went up um, minus 11, so that means this was 59. 59 was never going to happen here because nothing times 8 is 59. So that's a complete dead end. That's a complete dead end. But here, 48. How did we get to 48? We could have gotten there from 57. How did we get to 57 from here? Well, it's probably another loop on the 48. So that's like 66 from here. No. How did we get to the 50, 40? It was from, so we subtracted 4, right? We could have subtracted 4. We certainly didn't multiply by 4, and we didn't add from here either, because that implied like we had a 53 there. That's a no-go. But to get to this 57, we had 66. 66 minus 4. No, not 66, sorry. 61 minus 4 equals 57. And we got to the 61 from 68. 68 is sounding familiar. So 68 minus 9 to 61 minus 4 to 57 minus 11 to 48 minus 18 to 30. Okay, so there's a path there. Can we get to 68? So I think we can actually. Right, because we can get to 60. How did we do that? 22 minus 4 was 18. Times 4 was 56. Right. And plus 4 is 60. And then plus 4 is 64. Plus 4 is 68. Hey, so we found another path. What was that path? So 22, 18, and times 4, 56, 60, '64, 68. And now from 68, we go down 11 and 20, down to 48. So minus 11, and then minus 9 gets us to 48. Minus 18 equals 30 times 1. So there's a solution. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Well, there's an 18 solution. And it's giving me an insight. Does this give us the wherewithal to try a Volt 2? Okay, let's try a Volt 2. And I think what I'm going to do here differently, we're going to BFS. We're just going to make an adjacency matrix. Basically for each point, we're going to say we can do these expressions, right? So from this point here, we can do minus 11, minus 18, minus 9, Oh, we're gonna do a lot of combinations. Hmm, would it be so bad to write that out? We would at least find it. I mean, yeah, from each place we can do a function. Um, Worst case scenario are these two. We could totally handwrite that. So val edge equals map from int to function of int to int. And Copilot has ideas but doesn't know what I'm actually doing. So point 0, 1, 3. This is actually a point. I suppose I totally could use the hash code in the map just directly. It does that anyway. So this is actually 0, 3. No, this could be a list of functions. I don't know. I don't know if I want to do that. Like this to -4 and +4. Okay, we have point. Now there's this one here. That's 1, 2. And we have a list of, we do +4 times 4. So +4 times 4 +4 times 4 times 11 minus 11. So times 11 minus 11. And +4 times 4 times 11 minus 11 minus 9. And that's it, minus 9. Identical. That's not bad. I'm already a quarter of the way done. I can actually do that. A little bit unconventional, I know. But maybe just doing it in a very different way is what I need. So 0, 1 this is going to be small. And this is going to be a list of times 8. Times 8. It's only times 8 or times 8. Times 4 or +4. Copilot trying to autocomplete this is annoying me. Okay, times 8 or +4. That's it. That's all you can do from there. 1. Yeah, it feels like something that you could do by hand. And then Zuno left a comment earlier that he saw or they saw their friend do it in 2 minutes by hand. I was like, oh, I might stumble into it. But oh, here we got it at 6 a.m. Okay, so this is the 8. The 8 you can multiply by 4, or you can multiply by 11, or you can subtract 11, or you can minus 1. And that minus 1's problematic. because that's terminal. Eh, we could always just filter out the paths after the fact, right? Also, how is this going to help me find the path afterwards? Like, I might compute it, but I might not actually find a path. This is silly. Um, what I could do is just rewrite my search strategy. Okay, let's leave that for a sec. Hold that Scala. This is reasonable. Like write an explicit BFS. I'm just feeling to see. I don't feel like I want to do the same thing over and just have the same issue, right? But like if it's a sneaky issue, that sneaky issue would just disappear in a different implementation that isn't prone to the same sneaky issue, right? Yeah, okay, let's try. So why don't we keep our model. In fact, while we're here, const and int case constant int. Okay, this time we'll track that. Const and we have n in there. Okay, so const is 22, const here is 30. You found another line 14 by hand. Cool. Oh, can I see that? So north, east, south, west. Wait, you can't do that. Northeast, southwest? Northeast, southwest. You're back at the start and it shatters. Right. Oh, northeast, east, southwest. Oh, okay. Right. North, east, east. 26. Um, -9. Cool. So it's a 17. And from there, we go north. So 21 plus 4, 25. South. Er. uh, what I should do is give me something that lets me kind of think aloud with this. I can input a bunch of commands and we just get the state at the end. I lost count. Um, So we could make the like next four states. So it says like def north. And see how the weight changes. And we can pass those along explicitly. And then next is just a set of all four of those. So for each direction, basically we take a new point. Let's do this. Def go p point. I'll make this private. So this gives us a new state based on where we've gone. And I'm just basically going to take this code here. And we do match on our current op. Okay. We can remove these comments. Those aren't necessary. Okay. This is our new state based on a point. So def north. Let's just do like n def n equals pos.n. So go pos.n. Yeah, cool. Copilot can autocomplete that. Def south. Okay, and then we can still keep this. Is the fact that I'm using a set instead of a list hurting us? It shouldn't, because it collapses those states. Okay, yeah, we'll try it. Let's finish this thought here. Next. So everything should still work the same here if we do directions. So aoc.dir .values.map pos.move in that direction. And then we go. So D, go pos.move D. And then that two set. Okay, cool. So that gets us the same thing, but now we have these functions. And we can generate something else altogether. So we can ignore that. I actually kind of want this in a worksheet so I can just play with a state and go in a direction. File3.worksheet.sc. There we go. We don't need a package anymore. We don't need that main. And we can unindent everything. Okay. So we can take our start state. And now, bad cop, I could verify your thing here. Okay, so start dot north gives me a new state. Yeah, with the weight and everything. So we can write start dot north. You made 29. Oh, okay. I can verify that. So start dot north dot east dot south dot west dot north dot north dot south dot east dot north dot south dot north dot east dot north. That's what I'm getting. State 22.02. Is that what you wrote? Northeast, east, southwest, north, north, southeast, north, north, southeast, north, south, northeast, north. My current code pushed? No, but you know what? I could just commit it all and let you have a look. And it'll be at that link. Sure, why not? Yeah, all the Synacor stuff. Worksheet, the README, and at some point I'll just force push that back to normal. And I think you'll want some of the untracked files too. Oh, don't look at how messy this repo is. I've let some experiments just stay. I should clean out this uncommitted stuff. Um, so all this Synacor stuff. That, 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 that. Okay, R8 snapshot. There you go. If anyone's looking through my code, I am really happy right now with how VM state is organized. Like if I deleted this implementation here and had you try to rewrite it, it'd be very hard for you to write bugs. You might even get it like on the first try. This is very much like if it compiles, it works kind of a scenario. Like if you're just browsing code, I'd look at VM state and inst.scala. But if you're looking at what I'm doing tonight, of course, that's a different story. Yes, so where was I? We're looking at the Vault 3 worksheet. And we want to try other things. Let's try some path we did. So start dot, we're going to follow this path here. East dot north dot east dot north dot south dot west. East dot north dot south dot west. Nope. Sorry, how do we start? East, north, and then east dot north dot south dot west. Okay. And that's the back and forth trip. And we do that 4 times. Oh, this is something different altogether. Right, that's not the thing from earlier. You can comment that one out. Start dot, we'll follow this one exactly. East dot north dot, we go up here, north dot west dot south dot, wait, north dot east dot south dot west dot east dot west dot east. What's the value there? At that point, oh, that is not what I expected. East, north, north. Okay, let's just go east, north, north, west. We want to go west there. East, north, northwest. Where does that get us? East, north, northwest. I suppose we could subtract more. East, north, dot south, dot north, north, dot west. Right, that's how we got the 56. Dot south, dot west. Oh, no, dot east. That gets us to 60. We can always do any multiple for at that point, or any multiple of 2 mod 4. So the one we want from here is 48. Yeah, we can subtract 3 times. Dot south, dot north. That drops us to 56, right? Oh, 56 again. There are probably faster ways to get down to this value. So that gets us to 48. That's one way to get us to 48. That's kind of slow. Let's try this one where we just add up all the way. So east dot north. No, I think that one was actually starting off with north dot east dot west dot north dot south. Yeah, we can just build up to 48 by going back and forth. In fact, there's a simple way. So we go north, and we go east west east west. So east, we just keep going west east over and over again, as many times as we need to. So from 30, we need to do that 30, 4, 8, 42, 46. Oh, that's the wrong parity, isn't it? $46, interesting. Okay, well, we can kind of basically get any number we want. I think just trying to get 14 in the fewest steps might be all we need to do. So here is one where we try and multiply by 4. So let's take this. This is multiplying east, north, northwest. So that's multiplying 18 by 4. 18 times 4 is 72. Yeah, and that's too high by a bit. But what if we subtracted a little bit first? So east, north, then you go south dot north first. Right, that's the 56. That's only 2 above 48. So from here, we've gotten to 50. Oh yeah, we've done this exact state before actually. We're at 0, 1. So we add 4 8 times. So we do dot south, dot east, dot west, dot east. That gets us to 48. Oh, no, that's the problem. After we multiply by 4, we still have to add another 4 before we can get to a place where we can subtract. But what if we needed to subtract 36, actually? Yeah, if we chunk our subtractions, that would work even better. So I wouldn't mind starting with something like a 72 then, right? So let's do 72 dot south dot east. So that is 76. And we can minus chunks of 18 dot east dot east. That is one chunk of 18. And then we can go dot west dot east, and that's another chunk of 18. Line 65, you don't want end s equals start, right? Because you never want to go to the start regardless of state. Yes, we don't want to go to start. But we're not going through start. Let me see. So are you looking at volt.scala? Line 65. Well, this whole thing is wrapped in a knot. So s.pos. Oh, yeah. So I want this end equal s equals start set. The very first one. It's okay if we are actually at the start with weight 22. If we're actually at the start, it's okay to be at the start. Like you shouldn't be disappearing right now, is what I'm saying there. You might have to squint at it a bit. It's not the best written, but I think I'm pretty sure that works. And if it doesn't work, the worst case scenario is that we are adding more states than are allowable. And that's not the issue right now. The issue is we're not finding all the states. Yeah, like if I delete this whole line altogether, it's just a filter, and it still doesn't work. Um, whoops, where are we running here now? Oh, was this from earlier? Okay, so here we go west and east again. That gets us to 40. We want to get down to 30 though. So 76 is a bit too high. This subtracts 18. Can we get to 66? In yay-ish many steps. Because at this point, 3, 2, 0, 1, 2, 3, 2. Yeah, we want to be 30. I mean, we could totally work with things like this. So 1 across, 2 down, or 1, 2, 4. So minus 4. Oh, no, that doesn't actually go to 50. Oh, that'll go to 48 eventually. Yeah, we would just have to do 4 times south north 4 times. 2, 3, 4. I mean, I could do so with all these transformations I'm doing. I could do some sort of graph compression algorithm and whatnot. Like, there's also this stuff I could do, but wouldn't be. The issue isn't performance. The issue is correctness. The issue is over pruning. So here's that north that gets us there. Okay, so this should be enough proof that the model is at least working, right? Wait. North didn't do that. I thought it's times 1. Wait, here we're at 48. Oh, no. We can't do it. Where is this 48 at, actually? 0.12. 1, 2. Right, 1, 2. We go east, rather. East. Okay, that gets us to 30, and then we go north, right? So that's one solution. North. I could move the filters up into here. Yeah, let's add the filters here. Okay, so we're gonna filter some states. These same filters here. Weight is greater than 0. Weight is greater than 0. Well, I mean, that's not gonna affect our current code, because our current code is here. We could make this an option of state and then filter on it. We have not tried knocking on the vault door. We have not tried any magic words. Friend or abracadabra. We have not tried going to sleep. I need to go to sleep. Well, I have a lot to sleep on, don't I? Oh, what progress did we make tonight? Jeez. End state has yeah. End state has constant 30 here. Luckily, we're not actually using that. So this is 1. You're right. The room is 1. That's just for display. It shouldn't do anything. I haven't even run this code, actually. Search here. So I don't think that was in this code here. Yeah. So that wouldn't have been the bug, but good catch anyway. Um, yep. It's sitting on const 1. That's basically, yeah, it's just the name of the tile it's sitting on. If you do current is not equal to end, how does Scala compute equivalence? For a case class, it's it's the values. If the values match. So basically, if this toString is going to be the same for both, then it's equivalent. Oh, your old big brain solution, or did you come up with something else now that you're trying? Um, BFS. We could do a BFS. So from a state, S state, and I don't know what we're returning. What are we returning? I guess we're returning an end state. Let's just return a state. We want a path to that state. I just want to know the cost. Let's do that for now. Let's just do int. We always change what it returns later. No, we don't want Copilot there because that's not the way I want to do it. So s.next. So it's the status states that we actually don't want that to be a set. Def next. Here, let's not make that a set. And we're gonna fold left on those. Fold left. So starting with our current state. Um, well, hold up. Basically, we're gonna try each of these, and if they are not the end, then we're gonna move on. If we're gonna do that, we are gonna need to move filters up into our next method. So this filter, def filter, oh no, dot filter right here. So weight is greater than 0. Weight is less than or equal to 0x7fff. Big orb. Oh, drop orb. Yeah, but when you drop the orb, it disappears. Yeah, I was kind of hoping it'd be a solution like that earlier on too. Um, so we have the weights. We have to filter this out. That we're not at the end position, but only in the case where we're not start. Uh, I guess there are other ways I could do this. I could just do a flood fill to rewrite plenty of those. S to some function, and we're just gonna copy paste these two functions. And honestly, we could put this in a valid, def valid boolean. So let's put all these methods into there. So S is actually just going to be this in all these cases. This, and here we go. This, this. And we just end all of these together. Whoops. Cool. Yeah, that works. So we're going to filter valid. Okay. Found array. Let's do a to list here at the end. Make that a list. Alrighty. We get the next states. Let's do a none here. None. And case. We're gonna fold this left into state, I suppose. If we are the end. So our accumulator is the previous one, and then we have a new state here. A new state. We'll call it n. Okay. So option dot when, or we're gonna do prev dot or else. So if the previous already hit it, or else n dot or else option dot when n equals end. Wait, no, we don't want to do it that way. Hold on. I think I just need to sleep. It's 7 a.m. Brutal. You said I haven't run Vault 3 yet? That wasn't the search. No, the search you've been seeing was Vault 1. Vault 3 is me making a refactor, and Vault 3 just has this code here. So all I changed about it is I just added in these north, south, east, west, so I could play around with the state a little bit and do a manual search. No one can do FP at 7 a.m. Nope. One last thing. We're gonna check if this here is actually valid. This thing I tried. Check my work. So this is a start dot east dot north dot west dot south dot east dot west dot north dot south dot east dot north dot south dot north dot east dot north. What? Okay, I mean, that was a failure there somewhere. And, I suppose I could do something like, I've got an idea. I'm gonna make a bunch of copies of this. We're gonna do some multi-line editing. Oops. Okay, look at that. I'm too lazy to program. 22, 18, 84, 73. So something happened. We hit this state 3, 2, um, with a value of 46. What happened once we did the south south? When we hit the south south, we landed at the 9. Huh. Something went awry early on. So we went down to 18. Then we multiplied by 4 to 72. Then we subtracted a bunch. 72. Oh, I think we added when I thought we were subtracting. Or no, I think. So this part here is going minus 11, minus 11, minus 9. We're subtracting like 20 from here. So we're supposed to hit 68 at this point. That's what we were trying to get to. When we do the south-south. So before we do that south-south bit, right here, what we want to do, I think that there's a rather luxurious amount of space for a dot operator, but I think C++ used to be around 64 to 256 calls in a single sequence. Oh my god. Okay. Well, I think I copied that down right, and it didn't do what I thought it was doing. Um, so I'm too tired to math. I'm too tired to type. I'm too tired to FP and solve this problem. So we'll see. I'm gonna stop, sleep, give it a proper think, and I'll be back when I have ideas. But thanks for sticking it out. Valiant indeed. I don't think it's a hard problem. I really don't think it's a hard problem. Uh, the other one though, the Ackerman problem that I forgot to return to. Um, I can't brute force it. And I was thinking for a second, I can't math it. But I don't have to math Ackerman itself. I have to math what this thing adds to it. Um, and how changing it changes the end result. And you know, if I could just get that running, that Ackerman, then maybe I'll see patterns. I might play around with it a little bit offline, but if I start to notice something, I'll pause and continue here on stream. All right, let's find a raid. Um, is there someone I know here? Good morning to you too. I will at least have a good sleep. It is vacation. Someone's making a real-time strategy in Godot. Could be interesting. We Linux game engine. Is this kind of related? Don't dream of grids all day. No, I'll have Ackerman dreams instead. Full stack development. Sunday cult meeting. Let's do a vibe check here. I don't know what this is based on the title, but I'll bite. Is it in English? For Sen. Oh my god, Zuna, you're still awake too. I'm sorry to keep you up so late. I don't know. I was having fun. The aggressions, even if they're not productive, they're somewhat fun. Bye and good morning. Um. All right. Any suggestions for a raid? Who should be raid? I don't know what's going on here. Fucking Eric. Well, see, the thing about Eric is normally we're off the hook by the 25th. Uh, Eric is striking from the grave, so to speak. Okay. I'm not sure what I'm seeing, but I'm liking this better. So let's give this a raid. Raid Pilata. All right. Hopefully we'll get it later this week. Have a good one.